CSIR 4PI. So initially we'll be having the few important invited lectures at 4PI, and in the afternoon we will be having a visit to 4PI HPC facility and some interactive sessions as well. So starting with the first lecture, so we have the first invited talk by Professor T.S. Mahesh. He's a professor of physics at Indian Institute of Science, Education and Research, IISER Pune. I'll give the brief intro of his expertise. So after completion of his PhD at IISc Bangalore, he did his postdoc at MIT and University of Dortmund, Germany. And his main expertise are in the area of intersection of magnetic resonance, specifically towards the nuclear magnetic resonance NMR and quantum information processing. And today the title of his talk is on quantum capacity, some potential avenues, and specifically examples inspired by spin, NMR, and NVCs. So Professor T.S. Mahesh, over to you.
Okay, very good morning to everyone. I begin with thanking the organizers for inviting me. It's a very timely event, and so we are in the quantum revolution. So it is also called second quantum revolution. Where the emphasis is on not on building the theory, but getting the applications, technology. So, but then when I got the invitation, I was not really sure what to talk about. So I just collected some examples, which I think have some potentials. So these examples are inspired by spin registers, especially NMR, nuclear magnetic resonance, and as well as nitrogen vacancy centers in diamond. So these are the two fields that we work on. So I thought some of these examples may initiate collaborations among CSIR as well as rest of the institutes, and may pave the way for further development. So all right. Sorry. Okay, so let's. Okay, so just to give some background, what I am talking about, I think we have a broad audience here. So let me just give some background. So here is the NMR setup, and we have nitrogen vacancy centers in diamond. So basically, these are all spin-based architectures. Okay, so there are spins, and surrounding that spin, we manipulate. In the case of NMR, so I will be describing a little bit in the next slide. So we have induction-based method for measuring the NMR signal, and here in the case of NV centers, we have optical-based method for detecting signals. Now, with these, we can do many things. So we use this as quantum test bed. Okay, so we can study quantum information, we can study quantum computing, we can study quantum control. I will talk a little bit about it, and we can do quantum simulations. That's another exciting possibility. We can study various phenomena, quantum transport, quantum foundations, and of course we can do future. We can do simulations of quantum machine learning and so on. Okay. All right. Let me describe a little bit about these things later, but first just to give a quick introduction to what I mean by using spins. So just to take NMR examples, so here we have a molecule. Okay, it can be any molecule. Okay, so and then we have atoms, and inside the atom we have nucleus, and nucleus has spin angular momentum. and we place that sample. Okay, so these molecules are inside this sample. We place the sample inside a very, very strong magnetic field, and I am sure CSIR people are well versed with NMR, but just to give a complete picture. So here we have very, very strong magnetic field, superconducting magnetic field generated by superconducting coils, and then we have surrounded by Helmholtz coil for detection of the signal. And now when we keep the sample in such a strong magnetic field, we have the interaction between the magnetic moment and the magnetic field. Okay, that's the Zeeman interaction, and due to Zeeman interaction there is an energy gap. And now, so this energy gap is proportional to the magnetic field. That's stronger the field, larger the Zeeman energy gap. And now spins can be in the ground state or in the excited state. So now there is an energy gap also. Now we can introduce transitions by resonant electromagnetic wave, and that usually happens to be radio wave in the typical magnetic field that we use. So that is the radio wave. It is like few hundreds of megahertz or gigahertz. Okay, so now so that is the resonant electromagnetic wave that induces transitions. Now good thing, okay, all these things are fine, but now what is the good thing? The good thing is, now this is a, of course spins are quantum systems, but now they can retain the superposition, quantum superposition, for long time. Okay, so this can exist in superposition of ground state and excited state for quite a long time, and during that time we can do various manipulations. Okay, so we can do all sorts of manipulation in a very controlled way, in a very precise way, and that allows quantum control on the spin dynamics. And from that superposition state, we can prepare arbitrary superposition state. We can extract signals which come out as NMR signals, and we can characterize and we can calculate back what was the state that we prepared, or what was the transformation that we applied, and so on. Okay, so that's the whole story, that we have quantum control on the spin dynamics. Okay, now once we have quantum control on spin dynamics, what are all the things that we can achieve? So that's the main story of this. Okay. Okay, so now what we can do, for example, we take this molecule. So this is L-histidine, and it has many spins. We selected some 12 spins here, and so it is called a 12 qubit register. It's a quantum bit. Each spin is a quantum bit because it's a spin half. It has ground state and excited state, and we call ground state as 0 and excited state as 1. So it's a, it's a binary logic. So it's a bit. Also it is a quantum system, so it's a qubit, quantum bit. And so there are 12 of them. So it's a 12 qubit register. And we can, you see, we can very precisely implement all these quantum gates on this system. And once we can implement all these quantum gates, so we can implement a quantum algorithm. Okay, so this together, it is called quantum algorithm. Just like classical algorithm, we can implement, these are like quantum algorithms and quantum gates. And finally, we detect. So that's the signal that comes out, and that tells us what answer to our question. We can ask many questions, and finally answer comes out. And it was proven, so over last 2 decades, that quantum computing can take shortcut to many of the problems. So for example, factoring, database search, and so on. So it is not the clock speed that matters. Clock speed can be quite small, but the route it takes is entirely different to find the answer. Okay, so it becomes far more efficient. And so that's about how we can simulate quantum computing. And so we can also use it for simulating various quantum phenomena. For example, in this case, we wanted to simulate a quantum phenomena and test it. That is called quantum time crystals. It was proposed in the 2010s. And then there were many arguments whether it can exist or not, and so proving experimentally was very important. And there were many experiments. Ours was one of the experiments. So we can again use quantum control on quantum systems to study quantum phenomena. Okay, in this case, we can show that it can show time crystal behavior. And we can also use it for some interesting computational task. for example, in this case, we wanted to do some kind of curve fitting or regression, and we can use this system. This is a very innocent looking adamantane sample. In solid state NMR, we use it all the time. Japanese scientists quite recently, they have shown that this can be used for computational tasks. In fact, they used it as a machine learning task for machine learning, and so they could do curve fitting using just NMR signals, and this can be scaled up further. I will talk about this a little bit later. And then, so another thing I wanted to emphasize is about quantum battery. So I'll be talking more about this later. So NMR systems can be used as a test bed quantum battery, and that is very interesting because it has a much faster charging rate compared to classical batteries, and then it can also give the energy later whenever required. Okay, so all right. So coming to quantum battery, so I think that is a potential avenue for further research. This is not yet fully explored. As far as I know, there is no practical setup, practical quantum battery that has been set up. So here is the idea that, as I said, so we have energy gap, right? So we have ground state, we have excited state, and there is an energy gap. Okay, imagine that all the spins are in the ground state. Okay, so that's the ground state of that system. So you can't extract energy from that. But now suppose, imagine that there is an excited state which is a metastable state, which is very stable. Okay, now suppose that we can activate that transition, okay, by some means, then there will be transitions. Okay, so I'm starting the transitions. So there are more and more spins in the excited state. Now come to this state. Now there are larger number compared to thermal equilibrium of spins in the excited state. Okay, so now I deactivate the transition. So now it is holding that energy. Extra energy is holding, right? It's that system has extra energy. So now that is like a battery, because now if you can store that state for some time, now it is holding that energy. Now whenever you want to extract, you again activate the transitions. Now it will again de-excite, giving out energy. Okay, so that's a battery. Okay, now of course in NMR this is what we call as population difference. Population difference is related to polarization, and from the polarization gives to signal, and from the signal we can find out which state of the battery it is. Okay, whether it is in the ground state, fully discharged state, or charged state. So that we can detect just by looking at NMR signal. Now, okay, so now not just that. Now, since it is a quantum system, it can be in a superposition state. It is not just up or down spin. It can be in a arbitrary superposition state. There is also energy in the quantum superposition state. Okay, so that makes it more powerful than the classical battery, because classical batteries are either in a discharged state, partially charged state, or in the charged state. But here, in addition to that, there is a quantum superposition involved, and that's what gives it extra power. So now let me just to tell you specifically what happens. Suppose we have these batteries, okay, and we are charging them individually. Okay, so together we charge some energy E. Okay, so we charge some energy EB. All right, together. And while charging, we are not interacting with one another. So they are not interacting with one another. So they are separately charging. Okay, so that is called parallel charging. Okay, so there is another charging scheme. This is called collective charging, where you put all the batteries together and charge together. Okay, put all the charges together. So it is called collective charging. Okay, in this case, they all interact with one another. And now it was proved theoretically recently that if you use this kind of Hamiltonian for charging in both the cases, in this case as well as in this case, if you let the quantum systems interact while charging, quantum batteries interact while charging, then the charging is quite fast. It actually larger the system, faster it is. It scales as square root of n, where n is the number of batteries and number of chargers. Okay, so it is larger the quantum battery, faster it charges. Okay, so that is very counterintuitive, but that was proven theoretically that this is possible in the case of quantum battery. So we wanted to test this experimentally. So we took many systems. So this has 3 chargers, this has 9 chargers, this has 12 chargers, so on. Okay, so the 18 charges, and this has 36 charges, and so on. Different molecules. Okay, so now we wanted to charge. So we activated that Hamiltonian. So that's a NMR pulse sequence for activating that Hamiltonian. It's called XY Hamiltonian, UXY Hamiltonian, and then we started charging, and we measured the charging ratio between parallel and collective. Okay, so that's the charging ratio, and you see that that scales as square root of n. So this is number of charges, and that is the charging efficiency. So that scales as square root of n. Okay, so that clearly proves that it is indeed a quantum battery that has this quadratic speed up as the size of the system. Okay, so that's a very unusual feature of quantum battery. Yes. Yes, battery itself is quantum battery. Charger is also quantum in this case. Okay, so that's the whole idea. That I'll come to that in the next slide. Okay.
Here in the NMR, you still need that cooling mechanism and other things, or not?
So cooling is required for superconducting coil only, but that is not the ultimate goal. So we have to take it out of NMR actually. So this is a proof of principle. Ultimately, we have to demonstrate it in non-NMR systems also. Okay, so yeah.
So the batteries generally hold the charges and it forms as current, so that use it as a current.
So it holds battery. In this case, battery holds energy, not the charge, not the electrical battery. This is energy battery. Okay, it holds in terms of charge. But this is a proof of principle. So we have to do something else to extra. Yes, you have. Okay, that's this. Okay, so now that's the answer for your question. So now exactly. So what is the storage time? Okay, so correct. So now here is the charging, and we have storage, and now we extract energy. So what we did was we have this. That's the battery. Okay, so we charged with all these 36 hydrogens, and then it is storing energy. Okay, and store it for some time. And then there is a load spin, so that is the next silicon. So that is considered as the load spin. Okay, so we use that as load spin, and we dump the energy to that load spin. Okay, that's this silicon, and monitored how long we can store. Okay, how. Yeah. There will be some loss, but it is roughly of that order. Yeah. So you see, it can store for about 2 minutes, and after 2 minutes, you still have 40% energy. So this is again proof of principle. You can say, well, okay, 2 minutes is too short. Okay, but this is proof of principle. But it has that quadratic speed up. Okay.
Yeah. Actually, the transition between two states.
Yeah.
So it is the difference between two states.
Yes, exactly. Yeah. Correct. I know. So usefulness comes in the next slide. Okay. So now that's what I am saying. Quantum advantage is evident. So we are just saying proof of principle. Okay. So it is in principle, nature allows that. Now you can ask many questions. Physics-wise, first thing we ask is, where is the resource? Why it is more efficient than classical battery? Okay. So we found that there are quantum correlations and all. So I'll not go into details today. So how much work can we extract? So that is another thing. Anyway, so that's the point out to your question. How much is the loss? And overcome oscillatory charging, because it's a unitary process. So if you wait charging, if you continue to charge, it will discharge, because that's a unitary process, right? Unitary processes are reversible. So if you don't stop at the right time, it will start discharging. So that is another thing. And then we can build can we build a quantum battery circuit? So that's another question. And how to discharge a quantum battery? So it is not trivial. So there are many aspects. Again, I will not go into this today. And then can we witness quantum entanglement using energy measurements? So that's another physics question. However, today what I want to focus on is in this quantum battery, so we can store microjoules to millijoules energy. So as you pointed out, whether it is useful, it is not. The mobile battery needs kilojoules. My mobile needs kilojoules. So you see there are some 6 orders of magnitude. We have to scale up. Now how to do that, I don't know. Okay, so we have to, so can we scale the energy storage? And also we have to extend the battery storage time by a factor of 100. So 2 minutes is not enough. Probably 200 minutes is beginning of useful stage. So that's what we have to do.
Actually, even 2 minutes is useful in some applications.
Maybe, yeah.
For example, suppose I don't have a UPS system,
Yeah.
without UPS. If suppose power goes off, this 2 minutes is good enough automatically to shut down my system.
Yeah.
So maybe there are some applications where this 2 minutes itself will be good.
So also another possible applications, at least in the small energy and short time, is perhaps in the biology, medical applications, where you want to deliver energy to certain cells and destroy them. And so I think in those applications, you need microjoules and short lifetime. It should go to the target and deliver energy. And yeah. Not electrons. So we are not storing charge, we are storing energy.
It is in quantum state.
Yes, yes.
So it is either you are exciting some electrons in an orbital.
Spin, yeah.
Spin.
Electron spin,
Actually,
yes.
These are
Yeah.
fermions.
Yes, you are right.
They are fermions.
Correct.
So if you want to scale up in kilojoules, most probably you will have to go to some bosons, spinless bonds.
So exactly, that is an open question. I don't have an answer today. Okay, so it may be completely different from NMR, because NMR has this problem. Yes, yes, yes. So we are saying that you are right. You are right. So we are saying.
Exclusion principle is there, which will take you out in a given state only to this thing can be.
Yeah, yeah. So this
possibly
is just a proof
sorry.
of principle. Yeah.
So
Yeah.
I think sitting in 4th paradigm institute, maybe a new paradigm could be instead of thinking about the mobile battery needs kilojoule because it's powering from one single source. Maybe we can think of using at the local energy supply itself. Individual components can be supplied instead of having one supply and then distributing it. So possibly new way of
Exactly. So it is making a lot of buzz actually, quantum battery, because it has the potential which is not yet harvested. So I think there can be. Yeah. Yeah.
How does speed?
Sorry.
How does speed lifetime of the molecule affect your storage time?
Yeah, actually that's what determines the storage time in our case. Yeah. I mean T1, T2. T1 determines, yes. So in this case, T1 is 2 minutes. 2 minutes, yeah. That's why we get 40% storage at the end of 2 minutes. Yeah. Sorry. If we can control the spin dynamics.
That's okay.
So that's the whole problem of quantum control. So how do we go to target state from a given initial state using those control Hamiltonians in the presence of all kinds of disturbances? Okay, so even if there are disturbances on the way, finally it should reach there. Okay, so that's the job of quantum control. And so that's what we did in this 12-qubit experiment, and so we could implement algorithm. And there are hosts of quantum control algorithms, and nowadays some people spend lifetimes on this, on quantum control, and still this is a hard problem, because as the system size increases, the Hilbert space grows exponentially. And so since the Hilbert space grows exponentially with the size of the quantum system, so now that is not enough. So we also have to have larger resistors.
I can use this mic maybe.
Give it to him.
Why this is coming like this, sir?
I think in his mobile and all things will be there in his pocket. He's putting in pocket, na? I think because of that only.
Systems, we can use it for large scale quantum simulations. This is one example I just gave, that is a simulation of time crystals. Time crystal, just to say in one line, it is same as a normal crystal. Normal crystal has spatial order, time crystal has temporal order. Okay, so suppose that a system has okay, suppose it's in some oscillatory mode. So this is in some oscillatory mode. Okay, so it keeps on oscillating like this. Now if it is disturbed little bit, it again goes back to that oscillatory mode. Okay, then it is called time crystal. Okay, like normal crystal, if you compress, it goes back to its original. It doesn't collapse. It goes back to its original crystal structure. Okay, it has rigidity with respect to spatial order. So time crystal has rigidity with respect to temporal order. Okay, so it has some oscillatory mode, but then if you disturb, it goes back to that oscillatory mode. Okay, it doesn't lose that oscillatory mode. So that's a time crystal, and that exists in nature. And again, there were a lot of debates whether it exists or not. In fact, that is an interesting story. But then now it is accepted that they exist. So we also showed there is a time crystal in this molecule. Okay. All right. Now one can also think about going for even larger sized spin register. For example, we take a crystal. Okay, it's, I gave that example of adamantine. It's a crystal, and in that crystal there are Avogadro number of spins. Okay, so as someone pointed out, can we use all those spins as a quantum register together? So it was proven, yes, it is possible. For example, in this work, they showed that there are 4,899 spins they could control. Okay, so it's and then they could show that there is they could study relaxation, decoherence, and all those things. So that is another exciting thing. So that is another approach. That is not enough. We also have to have long memory. As I said, it's all limited by T1 and T2. Okay. So this has been the story of NMR since the last 60, 70 years, that all the NMR systems lifetimes are limited by T1 and T2. However, that was so during my PhD also. Only during 2004, Malcolm Levitt, he said there is a way out. Sorry, this goes other way. So we can go beyond the T1, T2 barrier. Okay, so his title of the paper is Beyond the T1 Limit. Okay, so in fact, sometimes we think that there are certain limits, hard limits, which we can't cross. It turns out that there are roundabouts which we can go beyond that. And this was a wonderful work, and in fact it has opened a new branch of NMR. It is called long-lived states NMR. And so now you can see the resolutions. From this we can go that. Okay, so because we can cross that T1 barrier. Okay, so that can have wide-ranging applications. You see this, I mix up between spectroscopy and quantum information since I work on both. This has very nice quantum information way of looking at it. This is, in fact, this is a singlet state that lives so long, and this is one of the so-called Bell states or entangled states. And you can get millihertz resolution, sub-millihertz resolution in this case. Now, these things are not yet harvested completely. Okay, so there is tremendous potential for all these things. I think if we can work on these things, we can get something new. And also hyperpolarization. So we talk about nuclear spins, and nuclear spins have very less polarization. Of course, we can transfer from electrons. And where do electrons get this polarization? We can do optically. And so many of the groups are working on combining all these things, because nuclear spins have long memory but less polarization. Electron spins have shorter memory but medium sensitivity, polarization. But now we can use optical transitions, and optical transitions have very short memory here, but they can give very high polarization. And so by doing this kind of transfers, we can get long-lived and high sensitivity situations. Okay, so maybe I'll just skip some slides. I think I'm nearing end of my time. It's okay? Okay, okay, then I'll just talk about one thing. Sorry. Okay, so recently NV Center is making a lot of buzz. So basically, it is a crystal, diamond crystal. Diamond is full of carbon, so it's a carbon lattice. But then two carbons are replaced, one by nitrogen, another by vacancy. Okay, so two adjacent carbons are replaced. And so we have nitrogen vacancy center, and there is one extra electron sitting here. So it is called NV minus center. And this NV minus center has a very interesting property. This is how its energy level diagram looks like. If you excite optically by green laser, okay, so this is the electronic ground state. This is the electronic excited state. So now if you excite, initially there will be transitions from the electronic ground state to the electronic excited state. But when it comes back, it preferentially comes to one of the spin states. Okay. So these two are the spin states. In thermal equilibrium, both are occupied. Okay, so they are both occupied. But when you polarize by green laser, after some time, within about 100 milliseconds, only one of the spin states gets preferentially occupied. Okay, so this has because of the asymmetry in the downward transition. So that's a very interesting situation, because now you send a green laser and then you get spin polarization. Okay, so that's the interesting property of NV centers, and that has led to a large number of applications. Particularly, so this is for 10-qubit quantum computing, and particularly for sensing. So you can see that the NV center Hamiltonian has this magnetic term, so it can sense magnetic field. It has electric term, so it can sense electric field. It has it is not here. It has a stress tensor, so it can measure stress, and so and also it works in room temperature in ambient condition, no vacuum, no cryogenics, in all these things, and it can be integrated with chip. So that's the whole thing. So this is a very interesting system. Now, now if you can do hyperpolarization using NV center, you can hyperpolarize electrons or nucleus. You can do many things. One example is here. For example, MRI, current state MRI is limited by selectivity and sensitivity. That's why we need high field NMR. We need like 1 Tesla, 2 Tesla magnetic field, which are very expensive to maintain, as well as the initial cost. So if you can hyperpolarize, we don't need that huge strong magnetic field, because the spins are already hyperpolarized, so sensitivity is already high. However, still the spatial resolution is not good, and if you can do these long-lived singlet states, which are already very high resolution. And then we can get both selectivity and sensitivity together, and that can bring about revolution in the medical MRI, medical imaging. And so one can possibly do MRI with low magnetic fields. So in fact, one of my former students in UK, he's working on such things. Hopefully that will materialize in the future. Okay, so I think this is my last slide. I'm sorry if I have exceeded my time. So these are the topics that I just picked up as examples. There can be more. Now I am happy to take some questions if there is time. Address lines. Okay, you are right. Okay, so you are thinking in terms of classical computing, right? Yes. So here, in our case, the addressability comes from the frequency difference. So it is like we all have cell phones, but when the call comes, it comes to only one particular cell phone. Why? Because they are all frequency encoded, right? So same thing here. Okay. So nuclear spins, each of them, they have particular resonance frequency. So when you send that microwave, although it is there everywhere in the room, only that particular nucleus resonates. Yeah.
Hello. So during that energy storage, means energy is generated during deactivation or decay process. So actually, what kind of energy? It's in photon.
So when it comes out, it is a photon. Yes.
Photon.
Yes.
So that means when you are storing, you can say it as a photon trapping.
We don't say that way because I think normal photon trapping has different mechanism. See, every transition is like a photon trap,
then
right? In some sense, right? So you are trapping energy, right? So basically, yeah. But photon trapping per se has, I think, different.
If it will be in the same form, then you can say photon trapping. But I don't know whether it is
sorry.
transformation from some energy to other energy.
So here in this case, you are sending radio wave and extracting radio wave. Sending radio wave, storing
radio wave.
And then getting radio wave. Yes.
You can store it for
2 minutes. I showed in my example. It's
then why can't we say it's kind of trapping? Then if you are getting the same frequency.
Yeah, I think in principle yes, but I think that particular phrase is used in some context, which I am not sure whether it matches with that.
Okay.
Yeah.
Thank you.
Yeah.
Sir, is this experimentally validated or?
Which one? Quantum battery. I showed that's experimental.
Registers.
Which one?
Registers.
Registers. Yes, experimental. All are experimental.
So they are in room temperature.
Sample is in room temperature. Yes.
What are the other accessories required for this?
Right now we just use a commercial NMR spectrometer. Yeah. So you see, in one molecule, suppose there are 12 nucleus. We can individually manipulate all of them. That's why when I showed the gates, there are 12 lines. Yeah. Because frequency selection. Yes. Yeah. That is also challenging in scaling, and that's why optimal control comes into picture, and there is a lot of work to be done. I think that is the same problem in all. For example, IBM quantum computer, you have to send thousands of wires to control, right? Yeah. Yeah. Okay. So that is because I think in optical transitions, the spontaneous emission is very strong. Here, spontaneous emission is weak. Yeah. It's million times weaker. because that scales as omega power 4 or something, right? Einstein's formula. Yeah. Yeah. Yeah, I mean those things we can, yes. Yeah. So exactly. So if we have metastable state, then it is even better. Yeah. Strength of? So that depends on the Rabi frequency. So it varies from system to system. We use something like in terms of Gauss. It is very we refer in terms of the magnetic component of the electromagnetic wave, which is few Gauss. Yeah. Yeah. So it is like this. The way we detect signal is by something called induction method. Okay. So it is like a dynamo. So you take a dynamo. It has a coil inside that a magnet which is spinning. That's a dynamo. Right. It gives EMF. Right. Now instead of that magnet, you put nuclear spin. Now the EMF is proportional to how strong that spin is, isn't it? So if you hyperpolarize, it just becomes stronger. The polarization becomes stronger. No, hyperpolarization means you transfer polarization from electron to nucleus or optical to electron and so on, right? Okay. So you enhance the polarization. The the magnetic strength will be enhanced, and then when it spins by Larmor frequency inside the coil, it produces stronger EMF. So sensitivity increases. Okay, thank you very much. Yeah.
Okay, thank you so much, Professor Mays, for this engaging talk on quantum battery, quantum information, LLS. And yeah, I would request Dr. G.K. Patra, Director for PI, to give a memento as a token of appreciation for this talk. Yeah, let's move on to the next talk of the session, and it is by Professor Bhaskar Kanseri. I would just give a brief bio of Professor Bhaskar. Professor Bhaskar actually is a professor of physics at IIT Delhi, and he's also associated with the Optics and Photonics Center at IIT Delhi. And his main expertise in the field of development of photonic quantum technologies for free space and fibers, quantum state preparation, SPDC processes, detection and characterization, quantum optics, entanglement and topography, and quantum optics, etc. And the title of his talk is on quantum secure communication principles and applications. I have known his work since last about 10 years or so, and he will give the how he has implemented the quantum communication over the hundreds of kilometers of fiber. And looking forward to your talk, Professor Bhaskar.
Yeah, we will need this. We can use that. So, good morning. Can you hear me at the back? Yeah. So, first of all, I take this opportunity to thank the organizers for giving this platform where I think the largest group of labs of this country are present. I mean, it is presented by different people here. So I'll be talking not very specific about communication, but we'll try to give you an understanding that what are the basic principles on which quantum secure communication actually works with, and what kind of applications we are looking, because I see that the audience is quite diverse, but still I will try to put my best efforts to give you some understanding on quantum secure communication. Okay, So I think you have been already going through these quantum talks since yesterday, and already somebody has covered about quantum 2.0. So if you look into the development of quantum physics, like in the end of 19th century, the people who were working in physics were of the opinion that all the problems associated with basic physics are actually solved, and there is nothing for them or nothing exciting for them to start with. And there were only few problems remaining. One of them was the spectrum of black body, and also the interaction of light with matter. And these two were the problems which later on taken by several eminent people like Max Planck, Einstein, and all that. And the completely a new kind of physics has evolved over the last century, which we call quantum physics. So during the last century, whatever has been done was basically to understand the basic aspects of quantum physics, to understand its interaction with light, light as well as matter, and also to give some basic tools or basic understanding about the phenomena, which finally led to some applications. In fact, all of you are using smartphones, computers. They are all because of the revolution which happened last century, that is called quantum 1.0 or first quantum revolution. Now, since these have been quite successful, and much of the efforts has been to miniaturize the technology. In fact, if you go back to 60 years before, the computers were of the size of this room. And people came up with the idea to make smaller and smaller sizes thanks to the technologies such as integrated circuits, transistors. Now they are of the size of your watch, basically. Now the question is how far you can go. Can you miniaturize even further? And the answer is probably you can, but then the sizes will be so small that it cannot be explained with the classical physics. And invariably, you need to invoke what we call quantum physics or quantum mechanics to understand those phenomena. And not only that, there has been some early technologies which have been demonstrated, which have shown that there is a huge promise. In fact, devices which are developed using quantum technologies are way more potential, way more powerful compared with the classical technologies. And this is why people are trying to customize the technologies, and some of these customizable technologies already talked by the previous speaker, and also probably during the last day. So this is one of the big motivation over which these quantum technologies are actually relying on. So these are some of the technologies which are already shown here. I don't know if it works. Okay, it works very slowly. So there are technologies such as quantum computing, and you have already spent one complete day on quantum computing, so I will not talk about that much. There are quantum sensing and metrology, and these quantum sensing actually is in various aspects. There is a picture of what we call LIGO, Laser Interferometer Gravitational Wave Observatory, which is in US. And in fact, there is a LIGO India, which is also being developed in India. The goal is to detect astrophysical events with more and more sensitivity. And this quantum light, which we also call quantum states or squeezed states of light, they have demonstrated that you can increase the sensitivity of such very, very fine interferometers by 2 to 3 times. And that is called now advanced LIGO, which is quite promising for detecting those astrophysical events in much faster frequencies. There is also the technology such as quantum key distribution. So do I really need it? So there is a quantum key distribution, and here the reason is that since quantum computers are going to be very powerful, they are so powerful that they may break the existing cryptographies, existing codes which are being used nowadays, and then you need a solution where the technology which could resist those or could make those codes so powerful that even quantum computers cannot break them. And that is the idea of quantum key distribution. In fact, in my talk, I will more focus on quantum key distribution today. But overall, if you see, the trend is now we are going from quantum science and quantum mechanics to all quantum engineering. So you see that quantum computer, which is expected to be a very powerful machine and can solve many problems of humankind, it can also be threat to the existing cyber security systems. And it has been seen over last 6 months. If you just take some newspapers, you will see that there are various attempts. People are trying to, for example, some of the hackers are trying to use a new kind of attack, which is called harvest now, decrypt later. What it means is that they are storing this crypto text which is available now and waiting for quantum computers to be powerful so that they could use them and they could break those codes. At the same time, how it breaks, there is an algorithm which is called Shor's algorithm in quantum computer, which has no classical analog. And in fact, it has been shown that with a 133 qubit quantum computer, people have already broken 5-bit elliptic curve key. This is one of the security standard currently used for internet. So these are some of the instances where you can see that not only cyber security, but in quantum cyber security is going to be a very important area. And we need ways by which we can protect these kind of attacks, which will keep increasing with increasing the computational capabilities. And if you see, as I mentioned about CSIR, there are variety of labs with different capabilities. What essentially can be done is, can be made a supply chain, which we call a complete ecosystem, which can be enabler for quantum technologies. If you see the existing ecosystems, if I want to make a quantum communication solution, I not only require photon sources, which are being provided by some of the OEMs or manufacturers. We need photon detectors, which is completely from a different kind of OEM. We require cryosystems because for reducing the noise, we really need cryogenic devices. As at the same time also QRNGs and many of those. So this enabling technology is actually something which is making a complete ecosystem, and for realizing quantum technologies, this is actually must to have. In fact, I am sure that you must have seen this slide, because many of these technologies are of denial nature, and no country is going to give it to the other country. So there are indigenous efforts to develop our own technologies, and every country is having their own quantum initiative to do so. India is also coming with National Quantum Mission. And the goal here is essentially to indigenously develop these technologies over next 5 to 10 years time. So now at IIT Delhi, we are working on several domains of this quantum communication. We are working on free space kind of communication, where the goal is to connect either two buildings or two line of sight positions, and finally to scale it up for satellite kind of technologies, where we can use a satellite for line of sight communication. We are also working with fiber-based communication, where the goal is to be telecom compliant. That means whatever optical fiber we are using now, we could use the same optical fiber for quantum technologies, where we can send quantum signal and not only use develop the key, set up the key, but could also use the communication using that key on the same fiber. And also, because the heart of all these technologies are single and entangled photon sources, one of the attempts are to make them more efficient, more powerful, and with higher purity. And also with some of the colleagues in material science, we are trying to develop detectors as well. And the goal here is to be able to detect photons with more and more efficiency, higher and higher efficiency. So first the question comes that what is the problem with the existing security? Why we need actually quantum security? So if you, just for some basic idea that what actually we mean by this. So currently two types of securities are in existence. One is called the symmetric encryption, where both sender and receiver, which we typically call Alice and Bob, they use the same key. The sender uses it for encrypting the data, and the data goes to the other one, and the other one uses for decrypting the data. The same key needs to be distributed to both the users or L number of users. Now the problem here is that how to safely distribute the key, how the other party knows that which key we are using. And this has been the biggest problem, and one of the goals of quantum communication is actually to solve the key distribution problem. So the symmetric encryption is using trusted courier as of now. Like if you see different labs of defense or any other labs, there is only one organization which distributes the key. The keys are taken either in electronic form or some paper form by some person who is a trusted courier. And one can use one-time pad as well. For example, if you make a transaction through internet or online, you use a one-time password which comes through a secure channel, that is through your either email or through the mobile phone. As of now, it's a very fast way and uses low resources, low number of resources, and very, very secure. But the problem is that you cannot increase its security, because if I ask you to have a OTP of 100 digits or maybe 150 digits, it will be very difficult to use. So the other way by which our internet and digital world works is what we call asymmetric encryption, where you can have any length of the key. So that means it is much more safe in terms of the randomness or the number of keys being used. And it uses two types of keys. One is called the public key, by which the user connects to the a desired person or a website or a server. And there is a private key by which the server can actually access that one. And the interesting part is that there one uses, as of now, some very, very complex, computationally complex problems to solve. For example, the product of large prime numbers. A existing computing capability, even HPCs, may take years to solve such kind of problems. But the condition is that a quantum computer using several algorithms such as Shor's algorithm can do it in fraction of second. So the moment a very powerful computer comes, which are actually being built across globally, this problem, this kind of security will actually go away. And here is the thing where we need a completely different way of securing this kind of devices, and that is called quantum key distribution. So in QKD, or quantum key distribution, we use two channels. One is the quantum channel, through which can be a fiber channel, free space channel, or satellite, through satellite, that is through space. One can use photons, because photons are the fastest carrier of information. The speed is equal to the speed of light, what we call. And one can use any degree of freedom of these photons, which can be either polarization, that means you can use horizontal polarization, vertical polarization, or its superposition, or you can use other degrees of freedom such as orbital angular momentum or time bin, and you can send the information. Then you use another channel, which is a public channel, through which you make sure that the information has been randomly you sample and check whether the information has been securely received. If there is any change in the information, it is actually measured in the form of error, which we call quantum bit error rate, and we keep this rate below some threshold to make sure that there is no attempt of eavesdropping. And if somebody has eavesdropped or tried to take out the information, it will change the nature of these quantum states, so that the other party will get a completely different state, and that both of them can be alerted that, okay, somebody has tried to eavesdrop, and they can stop the communication. So the goal, there are two ways by which you can do that. One is called prepare and measure method, and the other one is called entanglement based method. Now the yes, please. I will come to that. So I think as I go along, many of your queries will automatically get sorted, because they are coming into the next slides. Okay? So now the beauty of these quantum states is that, so if, for example, if you have a classical information such as a page of paper with something written, you can identically make multiple copies of that by using a photocopy machine. There is no problem. But the moment you have a quantum state, for example, you have a unknown polarization, which is in C part here, since you don't know in which direction the polarization is, you can only make copies of horizontal and vertical, but not at a diagonal, because you don't know at what position it is. So that way the quantum states cannot be perfectly copied. So this is one of the key idea which is used in case of communication, the secure communication also, where you can actually know that somebody has eavesdropped. Now I mentioned that there are two types of these communication methods. One is called prepare and measure. Here the Alice is the one who prepares a state, who prepares the photons, it is called transmitter, and Bob is the one who is receiving the states. And typically these kind of methodologies are coming from classical sense, just they are trying to make it compatible to the quantum world. For example, you can take a laser beam, can attenuate it significantly that it looks like a single photon, and you can do communication with that. On the other hand, there is another way which is called entanglement, and entanglement is truly a quantum feature. There is no classical analog of that. So if you could generate two states, which are two photons which are entangled, and send both of them to Alice and Bob both will be the receivers. They will receive these photons and will then set up the key. So in that case, you can get many of the features which are way more robust compared to the previous case, which is prepare and measure. However, since there are also shortcomings in entanglement-based QKD. For example, they are not very efficient as of now. You cannot generate entangled photons at very high rate. Your key rate will be very low. So we actually use either this or this depending on the requirements. If you need very high security, you would use entanglement. The good thing is that if you could make it based on entanglement, it will be a completely unhackable solution. Even a source, even if it is with adversary and it is generating entangled photons, it is perfectly safe. Nobody can basically change the nature of those photons. And you can have many exotic applications such as quantum teleportation or quantum repeater using entanglement based strategy. So in past we have been actually working on both the streams. I will give you one example of each of them. And we started with fiber based communication because if you see globally, there is more than 1 million kilometers of fiber being used for your internet, whatever we are accessing now. So that means fiber is a very strong and very, very important media by which we can do communication. So can we use fiber, that is the existing fiber, for quantum applications? That was the goal. So we used a protocol called distributed phase shift DPS protocol. Here the idea is that we generate pulses which are randomly modulated, phase modulated by either 0 or pi. These are sent through a quantum channel to Bob. Bob is the receiver, which uses an interferometer, which is 1-bit delay interferometer. That means we are interfering every pulse with its next pulse or previous pulse. And then we finally get the detections on either detector 1 or detector 2. So in case of Bob, depending on the detection, it knows that whether it has been, the phase difference has been 0 or pi. And the timing information, if it sends to Alice, looking into the timing information, Alice also knows that what was the phase which has been given to those instances. So that way both can set up the key. So this is a very, very robust protocol. In fact, it is based on phase. So in fiber, it is perfectly working very nicely. And it has been also shown that many attacks cannot stand with this because it is actually working on difference of phases, not absolute phases. And that's why the attack, even if it is attacked, it cannot get the information. The eavesdropper cannot get the information. So we did those realizations as our first realization. So we first made a transmitter and receiver based on this protocol, and we tested it in our lab. We took it even in the field where we put our transmitter at Prayagraj, which is what we call Allahabad earlier. And there was a fiber which was 100 kilometer underground between the cities Prayagraj and Vindhyachal. So Vindhyachal was the receiver. The length of the losses within that fiber were about 26 dB, and we have shown that we could actually get a key rate of about 10 kilobits per second with a Q bar of less than 9%. And this was the first intercity communication in India, and DRDO was our partner in this activity. Then we also asked the question whether this is the maximum length we can use this protocol or we can actually exceed the length. So we worked on several aspects of optimizations, improvements in terms of different aspects which were actually contributing to the quantum bit error rate. And we reduced it so drastically that with the same scheme, we could actually show a length of 380 kilometers, if you see the last line of this data, and with an error of Q bar of less than 1.5%. So this has been the largest distance so far achieved with this protocol globally for a very minimum Q bar. So basically you can go for very large distances with this protocol, but ultimately after this distance you again need to put some repeater. You cannot go beyond that. So trusted nodes or repeaters you essentially require with this, and since the quantum repeaters cannot work without entanglement, this protocol have certain limitations. So then we thought that, okay, let's use some more exotic properties. One of them is called spontaneous parametric down conversion, where which is a way to generate quantum correlated photons or even quantum entanglement. And here a very intense pump beam interacts with a second order nonlinear media and probabilistically gives birth to these pair of photons which we call signal and Idler, and they are quantum correlated. So basically if one signal photon comes, it is always accompanied with one Idler photon. And one can actually generate entanglement out of this. So quantum entanglement has been a very fascinating subject, and initially people could not understand it much. There has been a lot of debates, but finally people not only generated it but also showed its applications in various areas, for which these three gentlemen got Nobel Award in 2022. So I will give you a brief example how it actually works. Imagine you have an entangled photon source where you are getting two photons A and B, and they are anti-correlated in polarization. Now I can take these photons anywhere in in the world. That means I can either take one photon in India, other photon to US, or even to other galaxy, and I can try to make a measurement of their polarization. So in every attempt, if I make measurement of one polarization which comes, say, horizontal, it transmits, the other one will automatically reflect because they are generated at anti-correlated way. And in the second measurement, imagine that I get it reflected in the first, the other one will be transmitted. So these are non-local correlations which always exist irrespective of the distance. And you can use those correlations for various applications. For example, you can use them for quantum communication, entanglement-based quantum communication we call it. And it gives you an extra layer of security because it is not there in case of prepare and measure kind of protocols. So now what we do that we generate, the quality of this picture is not good. So we use this entangled photon source. We send one photon through an optical fiber spool of 50 kilometers, other photon to the other spool, and we try to measure that after this 100 kilometer distance, do they still have entanglement or not? And we demonstrate here, you can see that for 100 kilometer, we still get a visibility, which is visibility of this entanglement more than around 80%, and the threshold is about 71%. So that means that even after 100 kilometers, they are entangled. So entanglement can be distributed, and you can actually do the QKD also. You can extract for different distances the key rate. And in our case, for 50 kilometer, for example, we got 1.4 kilobits kind of key rates. We also tried to see, because this was in a lab setting, that is a fiber spool, if we use a real underground fiber, would it still work? So since in Delhi it's not very easy to get those fibers with low losses, so we could get one within the campus which was being used for this internet. So they were kind enough to give us one spool or one round of fiber of about 8 kilometers. And we have shown that for about 18 kilometers, because the other side we put 10 kilometers to compensate for that, we could get a key rate of about 2 kilobits per second with a Q-bar of less than 3. So that means it is actually compatible with the field settings as well, and we can use it for any of the field related activities. One of our interest was also, because DRDO was the driving force in terms of funding, they were interested in the free space QKD, and so we also tried to make some work on this direction. And the idea was to connect two buildings of IIT Delhi. So this is a research and innovation park, and there is a main building somewhere which is not seen here in this picture, and to connect through this entanglement based protocol. So what we did that we generate the entangled photons, we measure one photon in one place, we send the other photon through a telescope, through a beam expander to the other direction, and we make measurement there, and we then try to see that whether there is an entanglement distribution in QKD for such a distance. So for 1 kilometer, 1.2 kilometer exactly, we did this measurement, and we have shown that for this also there is a key rate of about 250 bits per second with a Q-bar of less than 7%. Now these experiments are very difficult because actually if you really look into the physical settings, there is a playground here in between, and there's a lot of air flowing, so a lot of air turbulence is present. If you see our beams, see the typical laser beam, how it fluctuates because of these air flows and turbulences there. So despite that, we were able to to stabilize this and make measurements, and could show that the entanglement can be distributed for such kind of distances. So now, the next thing, since we have a couple of such demonstrations, the question is, can we make a quantum network now where we can use these all existing technologies which we have demonstrated? Before we go into quantum networks or quantum internet, let us look at how classical internet has evolved. So in 1950s, when we had the first type of electromechanical computer, thanks to the development of these transistors and ICs in the next decade, and also some protocols in the next decade for connecting these computers, by 80s and 90s, we had the first Mac systems ready, which were also connected with internet in 90s, and that is the internet we are also using nowadays. In a similar fashion, if you look about quantum things, during the last decade, the first type of quantum computers, which we call annealing type or D-wave, they were present. This decade is very important because not only there are development of quantum hardwares and claims of quantum supremacies, but also that there are multi-node quantum networks which are also being developed globally. So we expect that another 10 years we will have some full stack quantum computer, at least usable computers would be ready. And then we would like to connect them securely through the internet. And the classical internet is not going to work because it works with bits. We need qubits, so we need a quantum version of that. And believe that another 5 or 10 years, a quantum internet would be really a need to connect all these quantum computers. Now, such kind of quantum networks which I am mentioning, these are not new things. In fact, China has been a leader in this direction since long. They started 20 years before us, and they have already set up a network of about 5,000 kilometers, which connects their satellite-based ground stations with the fiber and also several cities. So something that we are also planning to do under this National Quantum Mission, we call it Towards Trusted Node-Free Hybrid Quantum Secure Communication Network. In short form, we call it Tehqiqat, which means to investigate through research. So we have several organizations, IIT Delhi as lead organization, and we have 4 other organizations to set up this network, regional network of about 300 plus kilometers in fiber, connecting 4 states, that is UP, Delhi, Haryana, and Uttarakhand, IIT Delhi, and 2 campuses of IIT Delhi and IIT Roorkee, which are also having the free space connections in between. So we are actually aiming to use the hybrid technologies, because one technology is not a solution. And the goal is to have a scalable, programmable, and reconfigurable network test bed, which would be, when you take in a global scale, connecting all these regional ones together, would actually be a precursor for quantum internet. And this multi-node quantum network can find applications in various areas. For example, with quantum networks, we can do distributed quantum computing. We can have distributed quantum sensing. We can do several exotic tasks such as precise clock synchronizations, quantum repeaters, quantum teleportations. And also, it is not only for technologies, but also for foundational studies. For example, one can do quantum astrometry, which is a very, very new area evolving to measure optically the dimension of stars, and also quantum position verification, which is very much relevant because nowadays we are hear about GPS spoofing, GPS is being hacked, and also about the scams and all that. So it can provide a solution to these kind of problems once it is set up. I would also like to mention that we have co-founded a startup also to realize some of the prototypes associated with these technologies, which we have already shown proof of concept. And the goal is essentially not only to work toward quantum network elements, but also about the sources and QKD solutions, and also to contribute on skill development, especially by developing several UG-PG experiments where students can get in hands-on about quantum technologies and quantum technology related experiments. So with this, I would like to summarize that we started about quantum revolutions and quantum technologies, how QKD is developed and what are the different demonstrations, how entanglement works, entanglement-based QKD can be realized, and how these hybrid quantum networks are actually taking shape worldwide. So I would like to thank these funding agencies, DRDO, DST, National Quantum Mission, and the Institute of Eminence, IIT Delhi, and all these smiling faces who have been the main workforce behind these results. So thank you very much. Yes, please.
About the spoofing,
Yeah.
right, the last one which you mentioned.
Yes.
Even in the quantum communication channel, you can still spoof. You can, I mean, the most likely way the spoofing happened, at least in the Delhi airport kahani, is that there is a bright source which is directional and then blinds the weak signals which are coming.
Yes.
So
yes,
that's
yes.
much more easier to do in a quantum channel, right? The
Well,
spoofing.
as of now, I agree, because as of now we do not have, so these are kind of attacks. We call them attacks on quantum systems. But if we are talking about a quantum system and we need to characterize the attacks, we also have countermeasures for that. So what you are talking about, this blinding attack, has been a well-known attack for last 10 years. People have actually put isolators, different type of filters by which they can basically put a countermeasure for blinding attacks. What I was talking about is spoofing is that it was slightly different in terms of position verification, because, so for example, imagine a war scenario.
I just want to say that, like, so in the case of Delhi airport,
Yes.
it was precisely that, like, so it's the direction. It's not just one single satellite. The triangulation was done So you need the positioning itself has to be spoofed, or so that can be done with. You have to mimic the satellite signal and then use high intense beams focused in this specific area, so that like your 3 satellites or more than 3 satellites or signals are spoofed into the.
So it's a kind of a blinding basically. Exactly, I agree fully.
Blinding.
So, but what I wanted to focus on, especially in case of position verification, because as of now, for example, how scamming happens, like you visit to a server and you don't know where the server is positioned. It can be anywhere. It is just an imaginary space. Imagine that you could locate the position of the server by using position verification, and especially quantum position verification. Then you know that the server is somewhere sitting in the of the bank. So obviously your half problem is solved, that you are safe. The same way, in the war scenario, if a command comes to a launch center that launch a nuclear missile, and you don't know whether the missile command is coming from a command center or from some hacker's basement or somewhere. So if you could locate the position very carefully, and in a quantum network scenario, because we are talking about different nodes, all these nodes are working as verifiers, and the server or whoever you want to verify, if they are connected through entanglement through an ultra secure network, so this random blinding would not work, because you are only looking into those networks, and which cannot be attacked as of now.
So this will work only in case, even in case of free space, you are saying that you'll have the nodes which.
Yes, it is always with quantum networks, with nodes.
Because of the weak signals, you need to have nodes or
Yes. So we are only talking in terms of nodes, because in RF, it's much more broader. But in case of optical, it is narrowed down to the nodes. Yeah. Any other query? Yeah. Yes.
Okay. So this fiber-based communication, can that coexist along with the other internet connectivity, or you need dedicated connectivity?
So that's why I told in the beginning that I'm not going into technical, because so very recently we have demonstrated that this thing which you have seen.
That 8 kilometer water.
Yes, exactly. In the field fiber, which I showed you, we have done extensive studies, and we have shown that at telecom C band itself, we can put both classical signal and quantum signal on the same fiber.
Oh, okay.
And that coexists up to a very high power of classical, more than 100 kilometers, and there is no problem with coexisting of quantum and classical. So you can do internet along with entanglement. Both can coexist.
So still the properties.
Because actually the problem is the noise.
Yeah.
That is the Raman noise, if you see in more detailed way. And you have to suppress the Raman noise by not only just noise, but it is basically those accidental coincidences, what we call in technical terms, due to Raman. If we can suppress them by looking into the exact ITU channels where you should position yourself with respect to the classical channel, you can solve this problem. So that was more detailed, that's why I have not focused on that.
Okay. And the other thing is like this PQC one, which is where people
now so PQC is a. So there is no quantum on PQC, what we call in general, to be frank. So the idea is, so this is a quantum, so it is to make things quantum safe.
Yes.
And to delay, so that's, for example, in Indian context, there is the thing is that all classical things will be migrated to PQC for next 4-5 years time. But it is up to the time, then no algorithm comes to break those kind of algorithms. Suppose there are already calls on quantum algorithms, people are coming probably with new algorithms. So there could be possibility, there is no fundamental reason that why they cannot be broken in quantum case. And whereas this, what we are talking about, in principle, if you see, it is completely safe. But of course, every practical system is not same as the theoretical system. So there are always loopholes for attacks. And we have to find countermeasures for them.
Okay.
So this is all entanglement based. Yeah. Except the first slide, everything is entanglement based.
Compare this QBR with what the Chinese have. I mean, it's still
so
in the
Chinese
few percentage.
have satellite
have
thing. No, so Cuba.
They also have ground based.
Yeah, but then so actually, see, it depends on the type of fibers you are using, because many of their realizations are on ultra low loss fiber, because they have put a complete ultra low loss fiber, which is a change of complete infrastructure. They are always doing scaled kind of things. We have not even proper fibers available. So what we do is on these fiber spools. But then we cannot compare fiber spool results with the ultra low loss fiber, because there is a huge difference in terms of losses and like dispersion and all those things. So I mean, So the goal is actually to go for longer distances, and we are trying to put our own fiber now under this National Quantum Mission to connect this all on the stations. Probably then we will be in a better condition to compare, because we will have a 100 kilometer, 200, 300 kilometer kind of fibers. Then we could really see that where we actually stand on that. As of now,
Maybe
if this 100 kilometer you see, we are pretty good, because even in China, the maximum distances between two nodes is not 100 kilometer. That is 80, 90 kilometers in general. Yeah.
So maybe we should talk, because we are also interested for time dissemination.
Yeah, I know.
So,
So I have been already talking some of the people
so
there.
our locations are based on the legal metrology time.
Yes,
the regional centers.
True,
so
true,
maybe
true.
we can integrate the two to choose the positions. Right?
Yeah, sure, please. Okay, thank you.
Thank you, Professor Bhaskar, for such a nice talk on quantum secure communication. I would request Dr. Venugopal Achanta, Director NPL, to give a token of appreciation to our distinguished speaker.
He's a PhD from NPL.
Okay, and yeah, let's disperse for the high tea, and yeah, just for 15 minutes, and after that we'll just assemble here, and then we'll start the next session.
Yeah. Hi, sir. I hope you are able to see us and we are audible to you. Okay. Just give me a minute. We are getting started in a minute with some arrangements. Yeah.
Do you see my screen?
Hello. Yes, sir. We see your screen. Good morning, one and all. Once again, welcome to the post-IT session of CSIR Quantum Conclave 2025 CQC. And the next speaker is Professor Sanjeev Senapati from IIT Madras. I will read a just brief bio of Professor Sanjeev. Professor Sanjeev is actually a professor of biotechnology at Indian Institute of Technology Madras, IIT Madras, and his expertise is in the protein dynamics, green chemistry, and nanoclusters. And his research is mainly focused in two major subgroups. One is towards the molecular modeling of enzyme substrate and enzyme inhibitor interactions. And secondly, he also works on the structure-based drug discovery. And sir, looking forward to your talk on a framework to solve protein folding problems in quantum computers.
Thank you so much. Looking forward to some last minute comments. Oops. Okay. Hello. Yeah. Can you hear me?
So, yeah, you're audible, but are you presenting? You can go ahead on full screen for your presentation, sir.
Is it visible now?
No, I guess you have opened multiple windows here. You can go to your presentation window, sir, and make it full screen. You can close out other windows.
Yeah, that is what is saying in my machine. Just give a second now.
No, it is from his end. Yeah, yeah, this window. Please stay on this window and make it full screen.
It is going very slow.
Is there a network speed issue, sir?
I think so.
I think you can just log out and log in one more time.
Yeah.
Yeah, better.
Can you slide us? Yes. Okay, I guess now. It is hanging. Can you just open this? This is hanging, right? This down.
Sir, is issue getting resolved or?
Not yet. I'm logging out and logging in again.
Okay.
What is the problem? Is it a problem?
I think it dropped. Yeah. You're audible to us. We can straight go to your presentation window.
Is it visible?
Yeah. Yeah, that is the one. You can expand.
Full screen?
Yes.
Full screen?
Full screen.
Moving? Moving? Are the slides moving?
A little slow, but okay. We are still on the first slide of yours. You can turn off your video and just
Right.
yeah. Yeah. And let us test the slide changes.
Is it moving?
Not yet. There is network lag.
It's still not moving. Huh?
You can share the screen, complete screen, not the window, sir. Share the screen.
Right. The screen is there.
And then let us stay on slides.
And to join through another computer, just check if that is coming better.
You just share your slides to us. I'll just ping you the mail ID. Then we can actually present from here and we can talk. Yeah. but then yeah, that. Okay.
Now I would suggest let him not use the full screen. Let him use the slide change mode, not the slide mode, presentation mode, and keep switching to the slides and then see if that's better.
So there is one suggestion. We can stay on one window, not in presentation mode, but the slide mode, and you can actually go to the next slide this way. The one which is open on your screen, right? You just full screen it, and you can actually go down slide by slide. Yeah. That would be, won't consume much network. Am I audible to you? Yeah. Yes, why not?
Yeah, all right. Okay, some kind of breaking news what we have had at CSIR. I thought, I'll take this opportunity while Dr. Sanjeev is trying to fix the technical glitches that are happening. This is a proud moment for all of us at CSIR. What happened yesterday was the CSIR NALs, where we are sitting on their location, has come up with a self-powered high-altitude pseudo-satellite, which is actually very much called as HAPS. We had been working over that for a long time. My NAL colleagues are here. Actually, they can speak a lot more about it. But on this occasion, I am taking the liberty to share this, which is a happy moment for all of us, which is a pilot-free and battery-free floating UAV. It's an unmanned air vehicle, and that landed yesterday night in DRDO's test range in Chellakere, you know, and after that successful completion of 11-hour, 20 minutes flight during this winter at an altitude of 25,000 feet. Can you all believe this? It is a great achievement for CSIR, and it is a wonderful accomplishment of hard work of so many scientists, engineers, and other staff, which they put in so many a number of hours, and I don't know how much they put in, and because of which today we have realized this into a very profound result, and that's going to help our armed forces in a big way for our defense system. And this is a dire need from armed forces, and today when we have this, we are going to scale it up and try to also fix all those other issues, whatever are there, to go from here on to the next step, such that we find an industry partner and probably we'll push it out so that our defense system becomes more robust and more sound. So that's the video. Now the test, what had been done. Are we ready with the AV? Please go ahead with the AV. Everyone get the feel for the test landing that has been done by this unmanned vehicle, which is called as HAPS. That was actually, it was captured, the video was captured by a pickup truck that was chasing the aircraft, and one can hear that external pilot shouting out. So it was a very big achievement, and I'm happy that we could sit on the NAL campus and witness this. Thank you. 3 cheers to the NAL scientists.
Thank you, ma'am. So let us go to WebEx. I think he's joined on WebEx already.
Hello.
Okay. So while he's joining, I thought, I'll take another moment of all of you. I will be leaving at 12:30 to the airport, and this is basically I'm going along with Dr. Vegnugopal to Vizag, where at a CIA partnership summit, we are exchanging the MOU in the presence of Honorable CM of Government of AP for the Center of Excellence named as CQ-Tech, CSIR's Quantum Technology Center. And this we will be coming up as part of Amaravati Quantum Valley, which is going to be built in Amaravati, will be in the proximity of all the other startup stakeholders and other companies. So the Government of AP has earmarked 25 acres for this Center of Excellence. And this Center of Excellence is the vision of CSIR under the leadership of our DG ma'am, and that's where all of you would be contributing. So take it very serious while you formulate the proposals which will be funded and which will lead to this product development. And we have the stalwarts, the experts. We will be requesting them to guide us and also collaborate with the complementary expertises. And I am really very keen that this will go a long way. It's a long-term partnership. Tomorrow I'll be meeting all those startups in this quantum area also. The next thing what we will be doing is a startup hackathon, inviting the problem statements from these startups and also asking them to map our quantum group scientists. Actually, on this occasion, I should thank Dr. Saujanya, Dr. Swapnil, Dr. Vinod, and Dr. Asmita, where is she? All of them, and Dr. Venkatesh in particular, for keeping this whole thing happen. They are the guiding force and the working force behind this to happen. So I have to thank them. Give them a big round of applause. And thank you all for joining in, and I thank our experts for coming all the way. And we do have IBM and TCS partnership too. So let's try to explore these partnerships rather than build capability inherently. What we have is what we have as a strength, and try to use that for quantum enablement and quantum advantage to integrate and move on from there to build products in our own areas of expertise. Thank you once again to all of you.
Thank you so much, ma'am. So let us move on to the presentation we kept on hold for a while. Sir, we are able to hear you, I guess, and yeah, and your slides are very visible. So I think you're on second slide. They're changing also.
Right, good. Yeah.
Yeah.
Okay, excellent.
Thank you once again for joining and being patient during all this. Even the agenda shifted little bit. I welcome you on behalf of all our CSIR fraternity, all scientific and other staff. Let us go ahead with your presentation, sir. Thanks.
Thank you so much for giving me this opportunity. Sorry for the hiccups. So as Dr. Saujanya mentioned that some of you are interested to know how we are working on protein folding problem in quantum computers. And that is this talk about. I'll be giving a glimpse of where we stand and how quantum computers are helping. So why protein folding? We started with a protein folding problem, and the colleagues who are working in biological systems, biomolecules, all of you know that folding a protein is a very important thing in the function of our body. Protein folding is very relevant from neuronal function to for intact tissue and to protect us from different diseases. But due to external and internal stresses, the protein goes misfolded. And when the protein is misfolded, then that causes different kind of diseases. However, there is a mechanism in the body which basically tries for a misfolded protein to get into the right state of a folded form. And so there are certain other proteins called ubiquitin, proteasome system, and others which basically try to get the misfolded protein into the correct state. When the system fails, then different diseases occur. One such disease is called Alzheimer, where misfolded proteins, they come together and form a plaque. There are other diseases where misfolded protein is responsible, like sickle cell anemia and so on. So therefore, protein folding is an important phenomenon to study. In our group, we look at protein structure from different angles. We look at the structural biology, how a protein, if there is no structure, the protein, how that protein can be folded to a three-dimensional structure, which will have a lot of relevance in drug discovery, because drug discovery is nothing but designing small molecules which fits to a particular protein which is relevant to a given disease. So therefore, drug discovery, protein design, target predictions, in all this is very important that we got to know the structure of the protein. It is also important in protein-protein interactions because there is a downstream, upstream phenomena, and there many multiple proteins are involved in different conditions. So therefore, and there are certain proteins which are also important in designing the vaccine. So determining protein structure is very, very important. This is a current scenario where we use classical computers. So in the classical computers, some of you know there are two ways of looking into the protein folding problem. One is template-based, which is knowledge-based, based on our known structural data, and these are more statistical-based method. And AlphaFold is in good extent successful in predicting protein structure. Rosetta, machine learning, they're also pretty successful if you have the template available in literature. If you don't have any template available in literature, then all these techniques fail. And there you basically rely upon physics-based energy functions. Usually we solve Newton's second law, force is equal to mass into acceleration, and then you basically sample large-scale conformations, and by using techniques like molecular dynamics simulations, Monte Carlo simulations, you predict the three-dimensional structure of a protein and go on to look at its different applications. But now, some of all these classical techniques do have certain limitations, and many of you know about Levinthal paradox. So here is a simple example that if you have a peptide of 100 amino acids and assume that it can take 3 different states, so there are possibility of 3 to the power 1000 configurations. And if you even if every conformational change occurs in picosecond, the whole sampling the whole configuration space will take us 10 to the power 50 years. And so therefore it is not possible to look at the protein folding in classical simulations. The best computer available, the Anton from DSAW, it can at most simulate 166 microsecond, which is still far less than the second time scale, experimentally the time scale for protein folding. So given all these limitations, we thought quantum hardware can help, and Dr. Saujanya said that one colleague already spoke about different hardware available. So you must be aware of different hardware available in market, some are available in cloud, some you can buy. So we are working on IBM superconducting circuits, superconducting computers. So we have a tie-up with IBM, and now we have IBM hardware access. But now the question is, how do you utilize the IBM hardware? So in that regard, we started working on our very first problem was the simple, HP model. In a HP model, basically, we take we have 20 amino acids, and we segregate these 20 amino acids as hydrophobic or polar. So H for hydrophobic and P for polar. So we segregate the amino acids into two categories and wanted to see the very basic phenomenon of protein folding, which is the hydrophobic collapse. In hydrophobic collapse, in protein folding is basically the hydrophobic residues, so in my bit system, so what we did basically, we converted each amino acid into a bit. If it is a hydrophobic amino acid, we assign that as a blue bit. If it's a polar amino acid, we assign it as a red bit. And what you wanted to see the phenomena of hydrophobic collapse, where the hydrophobic residues will hide into the core. Given that our protein is in a solvent medium, so the hydrophobic residues would like to hide from the solvent, and the hydrophilic residues will be on the surface. We wanted to capture this phenomena by writing an algorithm which is efficiently run in IBM hardware. So after we coarse grained, we basically represented our peptides in cubic lattice. So there are different possibility of lattices. We started with cubic lattice, so we'll move to a face-centered lattice in the next problem. So we started with the lattice representation, and what we observed, so we taken different length of amino acids, starting from 13 to 20, and you can see we have a combination of hydrophobic and polar amino acids, and so these, for example, the first peptide, it has a total possible contacts, what you can count, would be 37. So these are experimentally counted contacts, 37 for this, 13 for this, 19 for this, and 50 contacts for 20 residues long amino acids. Now we did the calculation in IBM quantum hardware. We also did the calculation classically using simulated annealing. We calculated the number of contacts after we minimize the structure. We also calculated the radius of gyration, which basically talk about how the structure is collapsed, how compact the structure is. So you can see in quantum hardware, our contacts are very close to the experimental values, and is as good as the simulated annealing. If you look at the compactness is better in the IBM hardware than the classically predicted radius of gyration. And this is a pictorial representation. So basically, we started from a random, very elongated, very stretched configuration of the chain, and at the end, we basically get a compact structure where you can see the hydrophobic collapse. The blue are the hydrophobic beaks representing the hydrophobic amino acids, and you can see that the blue amino acids, they come together at the center, corresponding to the hydrophobic collapse of a protein. So this is our first work, and this got published in JCTC last year. This is a reference. You can have a closer look on the details of it. So this was a very toy model, the HP model. So we thought, let's go to more complexity, where instead of just H and P, can we have potential? Can we use the potential of 20 different potentials, or other pair potential for all pairs of 20 amino acids? So in that context, we came with a more complex representation, of the polypeptide chains, and this was the workflow. So it's basically the optimization problem. as we do in classical machine, we basically try to calculate the energy at different iterations, at different representation, and see how the energy is varying at different iterations. So it's an optimization problem. We do calculate the system both classically and quantum mechanically in parallel, and then we try to compare with the experimental structure. We also run classical molecular dynamics simulations to see how quantum simulated annealing and MD output are matching with experimental structure. So in classical, we basically use simulated annealing, and we minimize the solution, and we get this structure. In quantum, we solve the Schrodinger equation, where we need to first we have to encode. First, we have to represent our amino acids in qubits, and we'll speak more about it, how we represent the different bits, how we look at their connectivity in a qubit system. Next, what we have to do, we have to generate our Hamiltonian operator, and once we have our Hamiltonian operator, we have to also make an ansatz which represents the wave function, and then we solve H psi is equal to E psi to get the energy value, and from there, so we basically get the optimal structure. And then from there we decode the three-dimensional structure, and that we compare with the experiment, and we attain this condition. So this is our workflow, and this is how we do our calculations. So this is, as I said, this is a little more complex representation of an amino acid, where we taken FCC lattice instead of a cubic lattice. So if you look at this central amino acid, so this central amino acid do have 18 neighbors. There are 12 in the first layer, and there are 6 other neighbors in the second layer. So we have total 18 neighboring nodes, and each node is representing again an amino acid. So we have 18 neighbors, 12 in the first layer, 6 in the second layer, and now we have to basically find out the distribution of all the 18 neighbors with respect to this. So our ultimate goal is to look at the displacement between xi plus 1 with respect to xi and y coordinate and z coordinate. Now this 18 nodes, what we did, we divided these 18 nodes into 3 xy planes. So each of these planes, xy plane will have 6 nodes, yz will have 6, and zx will have 6 neighbors with respect to the central amino acid. So the xi plus 1, yi plus 1, zi plus 1, which is, let's say, this I plus 1th bit, its position can be obtained by this representation, where we are displacing xi by delta A, yi by delta B, keeping z fixed, because as I said, we are looking at xy plane or yz plane. So at a time, we are basically displacing x and y, keeping z fixed. Here we are displacing y and z, keeping x fixed, and so on and so forth. And this delta A and delta B are basically the displacement which represents with respect to the central node how much this node is displaced. So this and this are basically at a distance of 1 unit of lattice. This is at a distance of 0.5 unit of the lattice. So by delta A and delta B, by this representation in a FCC lattice, you can see how the 8 neighbors are distributed around our central node. So this is FCC lattice, which the physicists and some of you will be knowing. Now, big question is how we represent that distribution of nodes in a qubit system in IBM hardware. Now, as we said that we have 3 planes, and the minimum requirement of describing these 3 planes would be 2 qubits. So we have and those qubits we are naming as Q4 and Q5. For the XY plane, we are using 1 1 for YZ 0 1, and for ZX we have 1 0. So this is a binary 2 qubit system. So we have 1 1 0 1 1 0 and so on. So this is the distribution of the planes. So we require 2 qubits to represent 3 planes. Now we also have to represent the 6 nodes which are present in each of the plane. Right? As I said, that each plane will have 6 neighbors. So we have to represent those 6 nodes, and the minimum qubit requirement would be 3 to represent the 6 possible nodes. Actually, 3 qubit you can represent 8 possibilities: 0 0 0, 1 1 1, 0 0 1. 0 1 1 and so on. So you'll have 8 different possibilities, and out of 8 we need 6 only. So therefore we require total 2 qubit here and 3 qubit here. So we require total 5 qubits to represent this system. And that is how, okay, so if you remember, we had xi plus 1, yi plus 1, zi plus 1. So the new, the XYZ coordinates of each of the nodes. And now combining these matrices and the distribution of Q1, Q2, Q3, these are the three qubits to represent the 6 possible nodes, and Q4, Q5 are the 2 qubits to represent the planes XY, YZ, or ZX. So when you combine these 2 representation, we get the positional variation xi plus 1 minus xi, the distance between these 2 bits in terms of the 5 qubits which we require to describe the term. So you can see now xi plus 1 minus xi now is represented in terms of Q1 to Q5. So we are now we have now represented our positional variations of the nodes in terms of the qubits. So this is called the encoding. So we have encoded our lattices, we have encoded our amino acid bits in a quantum qubits now. So after the representation is done, the next thing we have to see the Hamiltonian operator, how we get the Hamiltonian. And here our Hamiltonian is nothing but the objective function, and that objective function is here. This objective function is nothing but the sum of Euclidean distances between all possible pairs of non-adjacent bits, and this is weighted by something called MJ potential. So as I mentioned previously, so we have this potential available in literature. So this is a statistical potential which basically tells about the pair amino acid, whether and how much contact they make. So it is a statistical based potential, pair potential, and that dictates what is the possibility of alanine and glycine to be together versus alanine and lysine not to be together. So this is my objective function, and our goal is to minimize this objective function. If we minimize this objective function, then we will get different conformation and their energy, and from there we will get the optimal structure. Now when we are making objective function, we also have to keep few things in mind, and those things we are basically using in terms of constraints. So here we have added 3 constraints. One is called the continuity constraint, which is C1. So continuity constraint makes sure that 2 neighboring bits are connected. We should not check for 2 bits which are not connected with other bit at all. So continuity constraint makes sure that bits are connected, the C2, which is the overlap constant, which makes sure that which makes sure that two bits are not overlapping. You know that amino acid I and the amino acid I plus 1, they should not overlap. So that boundary condition we put up. And the third condition we put the diagonal crossing to make sure that there is no diagonal crossing, meaning if you have bond between I and I plus 1, and you have a bond between I plus 2 and I plus 3, so these two bonds should not cross over. So with this constant, now our objective function is now ready. So this is the Hamiltonian that we that we design, that we model. Keeping so through this WJK, our potential is now, our Hamiltonian is now very specific for the 20 distinct amino acids. Once we have that, we basically solve variational quantum eigensolver, which minimizes pi h psi to give you the energy value. So here again, another unknown is the wave function, which we call unsuch in quantum jargon. So this unsuch, to start with, we basically take a random definition of an unsuch, which again we solve multiple times, keeping again this WJK in mind. So now we solve this equation using variational quantum eigensolver, and as you keep solving, we basically optimizing the structure, and then this will be kind of our output by solving the variational quantum eigensolver. So this is our output for a given amino acid sequence here by using PQE. Here, as you can see, okay, so this output actually came from IBM simulator. So this is a classical simulation. So as you can see, when you run it for about 2,000 iterations, initially the energy was pretty high, and from about 700 onwards, the structure became, the energy became minimal. So what we picked from here, we picked up one structure, and now we gone back to quantum hardware to further optimize that structure using about 4,000. We iterated to 4,000 times. And after getting all samples, we now basically converted back those output into classical XYZ coordinates, and those coordinates are now again shown here in a free energy landscape. And if you see how the contact energy versus radius of gyrations are distributed, you can see from here you can pick up different conformations. So I picked up different conformations from different space of the free energy landscape. So here you can see the free energy is the list, and the corresponding structure is here. Here green is the crystal structure, green is the experimentally obtained crystal structure, and blue are the structure that we obtained from our quantum calculations. So you can see here the match is pretty good. Likewise here, the RMSD is less than 3 angstrom. Since it is very small, so therefore RMSD is swinging pretty high because the compactness is less. And we also picked up certain other structures where the energy was a bit high, and there you can see the deviation is more compared to here. So this work also, the modeling of Hamiltonian unsuch already in the archive. You are most welcome to So this is one model peptide we taken. We carried on taking 13 other different amino acid sequences where we varied the polarity of the amino acid chain. In some cases we had more hydrophobic, in some cases we had more polar residues, in some cases we have longer chain, we have shorter chain, and then we compare crystal structure, which is again in green. So the left column is quantum comparison, and the right column is a classical comparison using simulated annealing. And you can see in quantum computers, our predicted structures are pretty robust. In most of the cases, our structure is matching very, very good with the quantum structure. Whereas, you can see here, the pink is simulated annealing or classical computer prediction. They are deviating much, much more than our quantum prediction. So the prediction is pretty robust. In this case, since we described using FCC lattice, and each bit requires minimum 5 qubit, and we have access only about 114 qubit, we could go up to 20 amino acids peptide. So if you we could go up to 4,000 iterations per amino acids. So nevertheless, you can see our optimized structures are pretty good. If you want to have bigger amino acids or bigger sequence, then we need better hardware as well as algorithm. So I think this is what I wanted to. So this is a glimpse I wanted to give that how quantum computers can give you results for simple amino acid sequences. So to conclude, we have shown that our algorithms work well in predicting protein structure and capturing energy lifespan. So here I want to stress upon that we have quantum hardware available with IBM, with DOF, with Google. There are a few companies. But what we, the Indian community, where our hardware is still not so accessible, what we can come up with is writing the efficient algorithms. So the hardware and software, when they go best compatible, efficiency can improve significantly. So in our work, we are basically trying to write algorithms which fit well with the IBM hardware. The both algorithms what I showed you, the first algorithm just for HP description, and the second algorithm is more complex, where we have 20 amino acids, rather air potential for all amino acids are specific for the specific amino acid pairs. And both algorithms work very well in predicting the protein structure or describing hydrophobic proteins. Apart from the protein folding, we are also working on writing algorithms for IBM hardware in predicting whole genome sequences. So if you are aware that we have multiple small chunk of genes available for a given individual. But the problem is how you join those small nucleotides together. How do you connect all those small genes together to get a whole genome sequence? And in classical computers, it is almost impossible to do it. What we are trying to do is that can we use hybrid classical quantum and predict the whole genome sequence given thousands to millions of small chunks of nucleotide sequence. we are also writing algorithm for virtual screening, and this is in tie-up with LNDB. So they wanted a quantum algorithm because to them, given so much small molecule available now in literature, even classical computer for virtual screening they find very slow. So we are working on quantum description, quantum algorithm to do virtual screening for small molecules. And this is what I was trying to tell. And quantum hardware is very expensive, and we pay about 80 lakhs to IBM every quarter. What we can do, we can write efficient algorithms which can reduce the number of qubits requirement. If we can use less number of qubits by modeling our complex system more wisely, our qubit requirement would be less, and therefore we can make best use of the hardware available. I would like to mention here that I haven't shown you the efficiency comparison. For all the sequences we've taken here, for this or even for HP, in terms of time, we are still not getting. Rather, if we have found that the sequence is 13 or less, quantum efficiency in terms of time is a bit better. But once it exceeds 13 or 20 amino acid sequence, quantum computer is taking more time than classical computers. But this efficiency again can be improved by writing better algorithms. So what we have to do, we basically have to come together, and therefore we require interinstitutional collaboration by bringing expertise from all of us to write better algorithms which can take the best potential of quantum hardware available. And I think many of you are aware of NQM, National Quantum Mission. There was a call from DBT last month, and we submitted one proposal which gone through the first hurdle, where my team came up with a team from TCG group, you know, the Chatterjee group in Kolkata. So they do have few scientists who work on, who are good in quantum computing. We have collaborator from ISC, we have collaborator from IT Bombay. So we need to come together to make best use of the quantum hardware available. This work was jointly done with Kalyan Dasgupta, who works for IBM, and he's a very our collaboration is going very well, very efficient, very effective collaborator. And the financial support came from Emphasis, which supports the center what we have at IIT Madras, a Center for Quantum Information Communication and Computing. So we have other verticals which work on quantum communication, quantum information, error mitigation, and so on. My group works on quantum computing and quantum correlations. With that, I'll stop, and I'll be happy to take any questions if you have. Thank you so much.
Thank you so much, Professor Senapati, for such a nice talk on protein folding problems. Yeah, we can take a few questions.
Hi Sanjeev, this is Mudit Dikshit from CLRI. It's a fantastic talk. The kind of work that you have done is truly great in terms of representation of protein and beads. But the problem that I was looking at is you can always compare the small peptides like calculating those energies and structures from ab initio post-Hartree-Fock methods. The gain that we are having even with the small peptide is not there yet. That's the first question. Second part, probably if you answer, I could. Did I?
Yeah.
Did I frame the question correctly? Did you follow, or shall I repeat?
No, I followed. Yes. You want me to answer question one?
Yeah.
First?
Yeah, please.
Yeah. So what you spoke about, those are optimization problem, of course, and that you can do in classical computer itself. Correct.
Correct.
But our goal is long term. At with quantum hardware available with qubits, where we have this superposition advantage, starting from small peptide down the line. Can we make use of this quantum superposition advantage for bigger sequences, for bigger molecules, so that ultimately we'll be able to sample much bigger conformation, which you cannot do in a classical computer. So this is just a starting point. As I said, that our goal is now to write the best compatible algorithm, which becomes best compatible with the quantum hardware. Once your algorithm is efficient enough, it make best use of the qubit, get best qubits, and you have qubits available. Your requirement of qubits to describe your nodes are less, then the quantum computer will certainly surpass the classical calculations. So at the moment, if you compare small peptide in classical and quantum, as I said, sometime classical is better. But we are looking for long term. In long term, certainly with better algorithms, with more availability of the qubit systems, things will go better for bigger systems, and that is our ultimate goal. We want to.
Thank you. Thank you for the great answer. Now, the second part is a little technical. The structures that you obtain and trace back to the original structure, did you compare them with the structures obtained from classical simulations? Like classical means force field based, or you compared with ab initio force field based structures? On this slide.
We did both. So we are expert in MD simulations. So the one what you see in here, what I'm showing is basically from MD simulations.
I see. Okay, thank you so much. Thank you.
Is there any question? Yeah. I think I should give it to IMMT because.
Good afternoon, everyone. I am Gurleen Kaur from CSIR Indian Institute of Integrative Medicine, Jammu. And regarding the quantum computing, my question is, and it goes along with the mandate of the institute, which is drug discovery and development. And I think it is worthwhile to mention here that CSIR Triple IM features a huge library of compounds, and we have around 90,000 compounds, including both synthetic as well as natural. So I would like to ask, how can quantum computing help us with the existing database that we have in terms of drug discovery? That is from hit to lead identification, actually precisely predicting the efficacy or the safety of these compounds.
Yeah. So all you can do in computer is basically, as you correctly mentioned, it is hit for the lead molecules. Toxicity and all this, as you know, that is beyond the scope of computational studies. So what do we do? So this is nothing but virtual screening, what you said. And virtual screening in classical computer in good extent quite successful. As I said in my concluding slide, that is another angle of what we are looking at, where given a structure of the protein, it is again an optimization problem, that given a structure, what are the molecules given your 90,000, which will have better free energy of binding. So we are working on that algorithm, and expectation is that we'll be able to come up with a set of molecules in a quicker span of time than classical computer. In classical computer, we do even larger libraries that we have available. But our algorithm is not yet there to make it better than a classical computer. But we see a scope. We see that we can do the virtual screening in quantum computer. But the toxicity and all these things, I think that is not possible in any classical quantum computer. Even though Sorin say they have software which can predict the toxicity, but I'm not so confident on their claim. But yeah, so virtual screening, I think we'll be able to come up with. And may I also ask you, this 90,000 molecules what you told, are these accessible to public? Do you have a database where we can try these out? Usually we use UK-based one database. If you have your indigenous 90,000 molecules accessible to us, that would be wonderful.
Yeah, these molecules based upon the agreement MOU, I think these are accessible to everyone. Yeah.
So IITM can sign MOU with CSIR?
Yes, yes, of course, yes. Sure. Two more short questions.
Professor Sanjeev, this is Dr. Balamurgan from CLRI. May I know whether you use these explicit solvents in your simulated annealing simulations here?
I'm sorry, your what?
Whether you used explicit solvents, water molecules in your MD simulation, simulated annealing, but in your quantum part that was. Sorry?
Quantum surely not. Quantum it is lattice based. So in quantum there is certainly no water, and that is why we have those boundary conditions. We have a constant of not shouldn't cross the two amino acids should not overlap. So by those constants, we are kind of giving implicit solvent environment.
Okay.
But when you run the MD simulations for comparison, so MD simulation does have explicit language.
I want to ask that you have started with the optimization problem, then you use simulated annealing, and then suddenly you change to quantum variational eigenvalue solver. So there was a disconnect, so I could not understand that.
No. So this is we want
Kalyan,
to see how quantum and
Dr.
classical
Sanjeev.
are faring. So this is two separate directions. So simulated annealing, we are making a prediction here. We are making a prediction how classical is predicting versus quantum. How quantum is predicting, how classical is predicting, and these two different predictions we want to compare with experimental structure, and that is the last slide. In the last slide, if you see, so blue is the prediction from our quantum, and green is the crystal structure, and in this column, the pink is the classical prediction. So these are classically predicted structure, which is in most cases not as good as the quantum prediction. So it's not that we are mixing. We are basically trying to see how quantum is faring in comparison to classical calculations.
Thank you very much, Dr. Sanjeev. Actually, Kalyan from IBM is also here in the audience, so he can elaborate more in next session.
Yeah. They are beginning.
Yeah, he is there even yesterday also.
Oh, I see.
Yeah.
Kargan is.
Yeah, he can be more explicit.
Ye-
Okay, thank you very much, Dr. Sanjeev. In spite of your really very hectic schedule, you could make it to us. This is very important because we have a very strong expertise across CSR lab in this protein prediction. So your inputs are very much important for us. Thank you very much for your time.
Thank you so much. It was very nice being with you. And I hope to see you in person sometime later. Yeah, okay, bye-bye. Can I leave the meeting now?
Yes, sir. You can leave the meeting now. And yeah, let's move on to the next session, which is interactive session. In that interactive session with the industry, and this session will start with a small presentation by QPy AI. Can we load the presentation? Yeah. So the presentation will be given by Dr. Sumanta Ghosh. Just give a brief introduction about him. He did his PhD from Indian Association of Cultivation of Sciences, IACS Kolkata, and his field of research is on electronic structure theory. And also his colleague Dr. Prakriti Singh, she obtained her PhD from CSIR IITR Toxicology Research, and her field of research is on toxicity of endocrine disruptors. Yeah, over to you, Dr. Sumanta.
Thank you for the kind introduction. So very good afternoon to everybody. As mentioned by you, I will try to finish it within that time. So thanks to Professor Mahesh, Professor Bhaskar, they have done excellent job in the development section of the quantum computing. I will briefly explain to how the quantum computing can be used for scientific discovery. Yes. So basically, we are a startup based in Bangalore only. We have situated in Bangalore, and we have 25 qubits superconducting qubits installed just in Bangalore. So this is the roadmap of our startup. So we are just here, and this is operational 25. Okay, thank you. So this is. Hello. Oh, this is operational 25 NIS qubits in 2020 from 2024, and the roadmap is like in the mid of 2026 we can achieve 64 NIS qubits named as Kaveri, and then 2027 this has been expanded to 128 and 1000 qubits in 2028. So that's the roadmap of our startup, and this. We are in the right track that 64 qubits superconducting qubits has been unveiled by our team with Prime Minister Modi in Bharat Mandapam last week. And this is 64 qubit quantum computing processor chips just visualized in the right side of the slide.
Are these fabricated in
Yeah.
India?
This is fabricated, like 24 qubits has been fabricated and 64 qubits is being fabricated. Yeah. So basically this is the scientific and technological advancement which is happening in the quantum computing domain, both in hardware, software and industrial domain. In hardware, the main complexity is the coherence time improvement, scalable qubit fabrication and error mitigation and surface cost development for like qubits to logical qubit development. And then there are software and algorithmic development that variational quantum eigensolver or the more improved version of variational quantum eigensolver to reduce the number of qubits for the particular algorithms like adapt VQE kind of thing. Quantum error correction and quantum machine learning pipelines, and these development like hardware and software development will lead to the industrial breakthroughs, most particularly in quantum chemistry simulation, quantum optimization for logistics section, finance section and healthcare division, and early integration of AI and adaptive circuit compilation. So as a quantum chemist and electronic structure theorist, this is a very interesting slide for me. Like in every lab, we struggled with these molecules when we solved it exactly. So this is the scaling, like for water, ethanol, benzene, glutamine, caffeine, and penicillin, the increased number of atoms. And like for classically, when you try to solve this molecule exactly, the number of the classical bits, you can see this is huge. And luckily, what the theory suggests, that for these big molecule we need 160 logical qubits. We are not 160 logical qubits era till now, but this is kind of kind of hope that if we can achieve this 160 or kind of 200 logical qubits in our hand, so we can simulate this kind of molecules, which is exact kind of thing. And this is also the scaling of different methods used by the quantum scientists. This is force field methods, which is fairly accurate, but exact is like that, which is exponential scaling. We cannot achieve here for a big molecule. And many scientists roam around here, like they tried to solve it by DFT or the gold standard CCSD. But CCSD is a single reference. So like for correlated systems or correlated electronic systems, you cannot get a better result using CCSD or CCSDT. So our goal is to like as first as DFT and as accurate or more accurate than CCSD. I do not know why this is missing. There should be a point. It is just like here. We want to achieve here with the in the NISQ era. So it, as speedy as DFT and as accurate as CCSD, or can be more than that. And when we can enter into that era of the fault tolerant regime, then the accuracy can be shifted here and the speed can be. So the dot can be shifted here. I do not know why the dots are missing here due to the PPT to PDF conversion, but this should be from here to here when you go to the NISQ era to the fault tolerant era. Professor was mentioning about the full stack quantum computing. So we are trying to build that full stack quantum computer in CUPA-AR, from algorithm, circuit compiler, scheduler, controller, and processor. Everything has been done in the CUPA-AI, and that can be like in every industry that can be scalable, from drug discovery to material discovery to process industries and automotive industries. Wherever you can find a optimization problem, this full-scale quantum computing system can be applied throughout the domain. So we have found out that CSIR has the expertise in a different domain, and they are very unique in industrial collaboration with different field. So we found out where quantum computing can be can enable us to collaborate with CSIR, and they can it will be a inter-institute or industry institute collaboration. Like in this biological science domain, quantum computing accelerates the protein folding, just shown by Professor, and enables bioprocess optimization, toxicology screening through quantum machine learning. In chemical sciences domain, simulates molecular structures, reaction pathway for drug discovery and catalyst design, optimize industrial process in electrochemistry, petroleum refining, and material synthesis. In physical science domain, quantum sensors achieve unprecedented precision in geographical, oceanographic, and metrology refinements. Then in engineering science, solves complex optimization problems, be it combinatorial optimization problem also. In aerospace designing, mining operation, and infrastructure planning, accelerates the material discovery for metallurgy, ceramics, and structural engineering. And quantum computing enables exponentially faster information retrieval, database searching, and pattern recognition in large-scale scientific data repositories. So throughout different areas, we can target where quantum computing can enables to drag the true advantage of the quantum using collaboration with the CSIR and these quantum computing startups and companies. So I'd like to introduce some of our platforms which we are trying to build, and these platforms are actually help to solve different kind of problems which can solve many problems in the industries. So we have QPI AI quantum platforms. This platform have platform access of QPI Gen 1, that is 24 qubits, and currently we are integrating with the Gen 2 quantum computer, cloud ID and development SDK. There are enterprise tools for the job management, organization control and credit tracking, and security and performance wise like enterprise compliance, circuit optimization, workflow automation also done in the QPI quantum platform. So this is one application by QPI AI. There is another application called Quantum Opt. This is basically a quantum inspired architecture which has multiple solvers like quantum solvers or quantum inspired solvers like QBO or QAOA kind of thing. And these are some performance metrics we tested for small system and small optimization problem. And these are some use cases, business problems, scientific research, and complex constraints. This is domain specific. Those are domain agnostic. These are domain specific like QPI Matter. QPI Matter can do different kind of tasks like catalyst discoveries, photovoltaic materials, polymer designs, high entropy alloys, different thing. And this is a platform which is currently enabled with the classical and AI kind of tools. Later we'll try to integrate with this quantum platform. Right now it is doing these technologies like DFT alternatives, AI accelerated platforms, discovery tools, and different applications I have already mentioned, so novel materials, functional design, and rapid discovery. This is again a domain agnostic platform which is associated with QPI Pharma, where like computational chemistry tools and computational chemistry calculations can be performed like geometry optimization, conformal search, transition state search, single point energy, IRC calculation, those kind of calculations which are hybrid AI, classical and quantum enabled. This platform is quantum ready infrastructure, AI workflows, classical HPC. Speed advantage is also there. This is not with the quantum, this is the hybrid approach like hybrid AI, classical and quantum. And this platform has focus area in drug design, chemistry calculation, and molecular modeling. And these are some benchmark of our calculations. Don't confuse, this is not quantum. This is a hybrid AI and classical and quantum workflow. Is the entire workflow which is we have got some speed up and obviously some accuracy and 0.07 EV error on energy gaps. And these are our QBO solver, QPI QBO solvers. So you can see our QPI QBO solver is doing great, and it is 100x faster than leading QIO solvers right now available throughout the industries. So this is our timeline. Like we have done this kind of things like benchmarking, cross validation with classical codes and skill trainings. Right now we are doing pilot integration with HPC and QPU, hybrid workflows, and targeted product prototypes. And after that phase we will enter into industrial workflows, standards, and more reproducible quantum IPs. Thank you for giving us the opportunity to present our work here. And yes, any questions I'd like to take. Actually, we would like to take. Prakriti, you can come also.
In fact, we'll take the questions during the interactive session. Yeah, please join us for the interactive session.
Okay.
And I would request Prakriti also to come, and Dr. Kalyan, please come. And our distinguished speakers as well. Yeah, please come for the interactive session. And then we will open for the questions from the audience. You can ask the questions from different. No, Kalyan will present if needed. I mean, if someone asks that kind of a questions, he will open the laptop and he will demonstrate. Yeah. So we will take the questions from different aspects, from starting from the hardware. I mean, the fundamentals. Professor Mahesh will answer the questions. And if you have questions related to quantum communications, Professor Bhaskar will answer those questions. And if you have any questions related to how to implement on IBM hardware, yeah, please feel free to ask. Dr. Kalyan will answer those questions. Yeah. Yeah, now we are open for the questions.
Yes, nice presentations. So actually my question, just before going to technical one, just a quick, very simple questions on this one. I think QP, your questions. So what are the initiatives we are taking for making it cost effective? Like what I understand, IBM is very expensive. Yes. So.
So not only IBM, every quantum computing company has done tremendous job in the R&D section, and they have put a lot of monies. I think when the qubits will be stabilized and algorithms will be refined to the problem specific domain, now it is kind of a domain agnostic algorithm kind of thing. Now when the domain expertise come into the play and they will place a problem which is which can be solved by the quantum very efficiently, then I think the algorithm sections will develop, and when that will develop, then the like qubits and algorithms both come into the play, and the price will drastically reduce. I think that will be the stabilization part. This is kind of exploration part now going on. Problem framing and algorithm development.
See, I guess there's some economy of scale as well, right? So right now, I mean, the cost of producing one quantum hardware is quite some, I mean, it takes a lot of money to build one hardware, right? And I guess when we have more adoption, right, more people coming in, I guess it happened with classical computers as well, right? So I'm guessing in time the prices will come down. Yeah.
And one more point, QPU, that is quantum processing unit, has it takes much less power than the classical computer, so that is where we can gain some advantage. Like I am talking about the real electrical power.
It's okay. So you are mentioning that it takes less power, but what I understood from yesterday's presentation and the conversation, actually it requires a high end of like cryogenic systems and other things to really run this machine. And when I just googled it up, like it says like it requires around like 2000, I think 20,000 joules of power, right? So do you think that it is some power?
Yeah, so I don't have the numbers, but all I can tell you is it's, I mean, this cooling or the dilution chambers are not that power expensive is what I understand. So it's not as challenging as a technology from the technology point of view and cost point of view. It's not that expensive is what I understand. I may be wrong. I'm not a device I'm an expert, but from what I've been given to understand, that cooling is not a major issue, cost-wise, technology-wise, both.
Maybe I can add on that. So far, I think yesterday it must have been discussed about different ways to form the qubits. And there are, superconducting is one of them, but there are others as well. And photonic is a one which is supposed to be room temperature. So whatever you are talking in terms of these cryogenic and all that would not be required in those cases. And there are already efforts going on in India itself to make photonic quantum computers. China has already built one, maybe 5 years before. So far the money is concerned in terms of those expenses that would be reduced, like power and all that in those cases. But of course it will take time because still there is no full-fledged computer available. So we have to still wait for some time for those things. Yeah.
RRI has done some work on that.
Yeah, there are so many. I mean, in a National Quantum Mission, ISC is having a thematic group which is supposed to make, which has already made about 6 qubit things as of now, but they are aiming to go for 25 qubits or something in near future, 4 or 5 years time.
Can you summarize this different superconducting,
I will try.
And photonic? Okay, very brief summary of.
I would have shown one slide, but I don't have now. So basically there are 3, 4 or even 5 different type of ways people are trying to do it. So for example, there is a way where semiconducting technology is also trying to make qubits. So if you look into National Quantum Mission, there are, each of them has gone one thematic group. There are 6 thematic groups, all are on different types or making qubits. Superconducting is the one and already ionic traps are the one. In fact, people with NMR, which is one, I think, I don't know if NQM has any NMR one, but there is also this kind of technology which is also going to make qubits. Photonic is one of them. There are several ones. In fact, there is no final thought that which one will win the race. Everybody has their own challenges. Every year they are trying to basically mitigate those challenges. So earlier this ion based one was leading quite a lot. Then superconducting suddenly crossed that. So there is always, they are coming with new technology, trying to make it more simplified so that they could add number of qubits. So the goal is to increase the number of qubits, go for logical qubits finally, and then to solve real problems, to show the quantum supremacy, what they call, like it is really better than a existing supercomputer or high power computer kind of thing. So these are all, they have their own benefits, like I mentioned about photonic. So photonic is room temperature. So that way it is very, very effective if you see. But then it may also have certain shortcomings in terms of interaction of photons with photons and all that. So, I mean, all have their own benefits, but also some limitations, and that's where they are actually playing with in order to achieve those large number of qubits, basically.
Yeah. So one thing is, I mean, it's a naive question. So, I mean, you have two entangled states and you are trying to measure them. I mean, don't you lose on your entanglement, and how do you, what is it you do to preserve those entanglement?
Measurement is meant to destroy, right?
So the question is, and I don't understand. So question,
you measured
after measurement.
Yeah.
No. So see, the whole idea is that quantum particles have the property that before measurement, they are in a superposition state. And when you make a measurement, you make an act of observation, they actually reduce to one of those projections. So for example, if I have a polarization entangled qubit, which is entangled, so I have two photons which are separated by some distance, maybe depending on how much you want, and they are on a state which is an entangled one. Now, we don't know what is the polarization of that state before the measurement. When I make a measurement, it projects to one of those outcomes which can be either horizontal or vertical. And that tells me that if one of them comes to horizontal and the other one comes to vertical, I know that there is a correlation which is between them. And any act of observation in between by eavesdropper will actually reduce in the middle itself. So at the end, you can know that, okay, it has already changed. And that tells us where we use it for this communication. So the goal of this distribution is basically to take them very far from each other and still retain the entangled property. And only the act of observation or measurement will finally tell us how they are correlated.
How long can you preserve this entanglement?
There is no such limitation. I mean, people say that even several hundreds, thousands of light years you can send photons.
I'm not talking of spatial, I mean temporal.
There is no temporal thing. See, they are instantaneous measurements. When I am making measurement in one, I am instantaneously disturbing the entanglement, so the other one has also projected. So now the act is instantaneous, but the timing, I mean, where they are can be any distance. So even if, I mean, people say that as long as light is being received from any star, if their photons are entangled, they will also be received. There is nothing to stop them.
Yeah, so I'm Sandeep from CSR IICT. I work in the area of mainly drug discovery using classical methods. So my question mainly for maybe Kalyan and maybe Sumanta can answer. So basically drug discovery, we can see there are three major areas where this quantum chemistry or AML can help. One is, I think, de novo design of drug molecules. So where most of the research papers are coming up, but I don't see that as a major challenge, because classical methods also we can identify hits very easily. Major challenge starts after identification of the hits, and what are the molecules when they go to the animal studies and in clinical trials, the more the molecule moves further, their failure rates are getting increased. So you can see one of the example like Alzheimer's disease, somebody has shown in the slides also. So last 20 years, almost 1,000 clinical trials happened, not a single molecule is approved. What is the reason? So areas like addressing the hit is identified, molecular potency is very nanomolar, but major issues are ADMAT, like absorption, distribution, and toxicity issues like hERG channel binding, then CP inhibition, mutagenicity, where you are not dealing with the one protein receptor, like we are dealing with multiple receptor, why toxicity is coming up. So whether this quantum chemistry can address those issues, precisely identify what is the reason for toxicity, and you can precisely how that heat can be converted to the molecule which is druggable and can be easily translated from preclinical to the animal studies. And second question, like whatever the molecules are failing in the clinical trial, all these multinational companies are investing a lot of funds, and after reaching to the phase 3 clinical trial, they identify that molecule is efficacious, but it is failed because of toxicity or poor therapeutic window. So those molecules can be give the life to those molecules by addressing precisely what is the functionality actually causing the toxicity. And we can give another life to that scaffold, because a lot of time, almost 10 years our efforts are gone into that to take that scaffold to the clinical trial, phase 3 clinical trial. Whether we can give the life and identify another molecule which can quickly move without that toxicity. So that kind of whether quantum chemistry can address this.
So yeah, in that way only, using the different quantum algorithms, like as you said, that identification of hit to lead is going to be easy. During that process only, when we are going to apply different quantum algorithm during the screening process, like in normal case we use for virtual screening molecular docking. So same way when we apply the there is a optimization algorithm, QAOA kind of algorithm. When we apply, we can find out the distance and how accurately ligands are binding in the pocket, how compactness is there while interaction of ligand and the whatever protein we have taken. So in future we can say that these algorithm is going to help us in very fast pace. So we can identify those critical compound, and simultaneously using different solver we can find out how we can reduce this ADME problem. Like major problem with the drug molecule exists there only. So in that domain we are continuously working. So how we can reduce the problem, or how we can enhance the absorption and distribution of any chemical without reducing their metabolites to creating the toxicity. So in that area only, quantum algorithm, when we are going to calculate the properties using this algorithm, so we can minimize these problems.
So are there any use cases where these kind of issues are solved by this quantum?
So recently few papers came out, but there are constant efforts are going on in this field.
Thank you.
Hello, I am Ashish Sharma from CSI NIRI. My question is from Professor Bhaskar, that my understanding is that to creating an entangled part, that qubit, it is very difficult process. So can you elaborate how you able to achieve that, and how you able to transmit to other place without disturbing their entanglement? Can you elaborate a little?
Yeah, so of course generation of entanglement is difficult, and not many groups in the country are doing it, but the whole idea is that so basically quantum entanglement has no classical analog. So you can do it in a very specific ways. For example, we are doing with a process called spontaneous parametric down conversion, but there are also some more processes. One is called four-way mixing, where you can do it in a fiber or in a material where you have Chi3 non-lattice, such as silicon, for example, chips, and all those people are working on. So of course it is challenging, but if we could first, before doing the experiments, if you could estimate theoretically that with what parameters, if you could model it and figure out that the efficiencies are good enough, then we can proceed for the experiments. And controlling, so for example, in our case, we are using not only crystals but also waveguides. In waveguides, since we can already couple them with fibers, so the problems of coupling are reduced significantly. Then we can do it much easier way compared to with crystals. But in free space, I showed you an experiment on free space thing. It is much more difficult because then you don't have any guided medium. So you have all kind of degrees of freedom. So of course it takes time. Like for example, students who have been working, they took probably 2 months, 3 months time to work with those crystals to find the proper temperatures, to characterize everything. But finally, I mean, as you know that, nowadays almost all experiments, if you read on these journals, they are using entanglement. So in order to be at par with global levels, we have to also, show some innovations in those directions. Now, your second part is that how can you distribute the entanglement? So for that, we need the channels, which is either fiber or free space, and they have their own limitations. For example, in fibers, it's good that it guides, so that is one thing, but at the same time, there is dispersion in the media. There are losses, there are leaking of signal from the fibers. These are some of the challenges you have to come across. And especially in case of polarization in fiber, the polarization can scramble. You send horizontal polarization, but ultimately you will get some circular polarization. So you have to calibrate, and you have to figure out timely every interval of time that what you are sending is actually being received by calibration. So those kind of things we have to do. We have to do it automated manner. In free space, it is much more challenging because we have turbulence, as I mentioned. So the beam also shifts from its direction. It wanders around some depending on how much turbulence is. So we have to then control, and we have to repeatedly send classical signals in order to make sure that the sender and the receiver is sending and receiving the same information. And also because the wavelengths we are working on are around 800 nanometer. And in the daytime, the sun spectrum has a significant portion of noise on those. So you cannot do the experiments in the daytime. So you have to live in the night time basically. And in night also, in the urban settings like in Delhi, you have so much noise pollution in the night, like everywhere lights are on. We are close to the airport, so we cannot send the beams toward upside, laser beams, because then there will be security problems. So there are several restrictions. But ultimately, because it's a challenge which we took, and we were able to do that. Yeah.
Thank you. I just want to add one thing. So technology is developing very fast, and nowadays UG lab kits are available to prepare entangled photons. In fact, one we have at IISER Pune. So we also have started the masters in quantum technology, where we have that setup. It's mandatory lab for them. As he mentioned, this spontaneous down conversion for preparing entanglement, it is quite a simple setup. And of course, utilizing that entangled pair is not as easy. As he said, it has to survive those long distances. But preparing and detecting entanglement, it's not easy. It's not difficult. It is easy. And in fact, we do this in NMR all the time. It's a old wine in a new bottle. So ever since NMR started working with two-spin system, we have been preparing entanglement without calling it as entangled states. Okay, so we were calling in as double quantum coherence, and basically they are entangled states.
Good afternoon. I am Vinita Joy from NAL. So mine is a layman question from the problem formulation point of view. So suppose if we are coming up with an algorithm which will be implementing quantum principles, how to assess the kind of hardware which will be required to solve that, and whether it is feasible to implement that with the existing scenario in our country as well as globally, to how to assess the feasibility of solving that problem with the existing conditions in our country.
Okay, so see, first of all, the thing is the Hamiltonian has to be there, right? And the encoding also needs to be there. So if you have an Hamiltonian, you have to see the order of your Hamiltonian, right? And first of all, the problem you need to see is whether your problem can be solved classically. Are you reaching the classical limit? Only then I think you should be thinking about quantum, right? So I'll tell you how it is done in superconducting qubits. So any Hamiltonian you have, you essentially break it up into Pauli strings, and it's easy to do all the expectation calculations, right? Even the encoding, there are several ways to do encoding. So if it's if the problem comes from a domain where you where there's some quantum alternatives to it. So for example, I'll tell you. So in chemistry, you have heard of the CCSD thing, right? So in quantum, you have quantum computing, you have a unitary alternative to that, the unitary coupled cluster. So there are some one-to-one mappings that you can easily do. But if there are domains like where you don't have this one-to-one mapping, right? So it's where your creativity or like your kind of your knowledge will come into play. Like so you have to be very see, right now the problem is you have some limitations in number of qubits and the depth of the circuit that you can simulate. So you have to be very ingenious in your way of in how to limit the usage of qubits and limit the depth of circuits. So there is some amount of creativity required. But more, I'm hopefully in the by 2029 when we have error corrected qubits and all those things, probably you don't need to worry about those kind of limitations. But for the moment, if you have to simulate your problem, you have to think on those terms. Right?
So we have to formulate the algorithm restricting the number of qubits which will be used for processing them.
Correct. So you need to, there has to be some unit in your system, right? That has to be mapped to the qubit states rather, right? And of course the Hamiltonian also has to be there, right? So those two things are very essential, very fundamental while formulating a quantum computing alternative to your classical problem.
So I can just give an example. This is an interesting question. So suppose, so this was a project done by one of our students, which also got probably one of the awards. He finally solved this using IBM quantum computer, and so some years ago. So the problem was to optimize industrial floor. Okay, so there is an industry which is a real problem actually. So he took this problem from some startup company which had this project to optimize the floor map for industry. They had various units, so there is a paint shop, there is a fabrication, there is something else. So they want to minimize the transport issues between the units. So they suppose paint should come next to something and all those things. Fabrication should come next to workshop and all those these things. Now given a limited area, now how best you put all those different units in the map. So this he had okay, it looks trivial. It is not, because when there are 100 units, already you see that so many permutations, combinations they are possible, right? So it is not a simple problem. And then the main trick is to convert that into, as he said, Hamiltonian. Okay, so it is done in most of the optimization task anyway, because you assign a cost function. Right, here cost function is energy. So you convert that into energy. Energy operator in quantum mechanics is Hamiltonian. Okay, so once you convert that into Hamiltonian, that's what one-to-one correspondence, then the problem is half solved, because now the problem reduces to finding the ground state of that Hamiltonian. Right, and that is efficiently done in quantum computer using various algorithms, variational algorithms, and different algorithms. So that's the way you convert any problem into a quantum computing problem.
So the Hamiltonian is the ultimate parameter.
No, at least for optimization, most of the things, because once you convert into Hamiltonian, I mean, if there is a cost function, okay, so energy is the cost now. You have to minimize the energy. So you have to find the ground state of the Hamiltonian. So most problems can be converted into this.
No, I mean, in quantum mechanics, you have to, at the end of the day, you have to measure some operator, right?
For example, it turns out that even factoring problem, Shor's factoring problem, can be converted into Hamiltonian minimization problem. Yeah. Yeah, most of the problems can be converted into this.
In the last slides, you can, professor was showing some FCC lattice, and there are some beads kind of things. So there also he was constructing a Hamiltonian, which is the interaction between the beads, like the hydrophobic interaction. So Hamiltonian is some addition of some interaction. So that is the process of Hamiltonian generation based on the problem statement. State generation. Ultimately, you have to get the energy, which is psi h psi divided by psi psi. So you have to generate the states, which is basically the quantum circuits and some operations in the quantum circuits, and you have your Hamiltonian. So basically, the state is parameter state, like it depends on some parameters theta, phi, depending what gates are you using in your quantum circuits, and you optimize those parameters and minimizing the psi h psi value.
So there are different methods, there is something called database search method. So Google is interested in not in Hamiltonian problem, but they are interested in database search. So there is a huge database and you are looking for some particular item, where is it? Okay, so it is like finding the name of a person whose telephone number you have. Yes. Okay, that's not easy, right? Because telephone directory is not sorted according to the number, it is sorted according to alphabets. So it's a reverse problem, and in such problems there are different methods. So there is something called Grover's algorithm and so on. And there is also another way, that is quantum Fourier transform based methods. So that is where Shor's algorithm comes
so
into picture. So there are different methods.
Yeah, so I'll expand on that. So see, right now the thing is, quantum Fourier transforms are very expensive, okay? So all these problems where you need these eigenvalue problems, right? So there are two ways of doing it. One is the variational way, and of course there's the sampling based quantum diagonalization, that is another way, but essentially there are like variational way, and the other way is basically going through the quantum Fourier, the inverse Fourier, basically it's something called QFT, I mean inverse quantum Fourier transform, let's say. So but the problem with those things are, although they are supposed to be very accurate, because every time you do the measurement, right, in using IQFT or inverse quantum Fourier transform, you're expected to get an eigenvalue. Whether it is the minimum one or not, you don't know, but every time you do those measurements, you'll get an eigenvalue. But with variational solvers, the problem is it's an approximation. So you're not sure whether it's an eigenvalue or not, right? So but given the circuit depths that we can simulate at the current moment, VQE is the preferred option. Okay, and algorithms that need, like the Grover and all, right? The problem with those algorithms, it's oracle based algorithms. So oracle is kind of you can think of a black box that magically gives you a 1 if your search is correct, or 0 if it is not. So the problem with oracle based algorithms is, like, you first need to devise an oracle, right? And you don't know how to do that for very, very large problems. So initially oracle based problems came up as a proof of concept, right? To show that, see, quantum can do this amazing stuff that classical will take a lot, the complexity in classical will be much more, right? So oracle based problems are a little tricky to handle. So I mean, Grover is one such thing, but yeah, I mean, again, there is some, I mean, you need to be creative in how you do make those oracles, right? So yeah, that is, maybe you can add something.
A quantum equivalent for that, if I can define it classically, right?
Could you repeat it?
Yeah, for example, I have an optimization problem.
Yeah, thank you very much. I have to leave because I have a flight. Thank you very much.
Thank you very much.
So my question is, yeah, can I continue?
Yeah, please.
Yeah, suppose I have an optimization problem in a classical sense, and I have very well defined cost functionals. So does that always guarantee me that I can always define a corresponding quantum Hamiltonian?
Yeah, so I'll answer that question. So the thing is like this. See, right now qubits work with ones and zeros, right? The states are always with ones and zeros. So whenever you have a quantum optimization problem, essentially you have to convert it into something like a mixed, binary integer linear programming. Okay, so that is a primary requirement at the moment. So this quantum, this protein folding problem that you saw was like, the states or the coordinates of the lattices were kind of converted into binary, units. So it was easy to directly convert it into a binary integer linear programming, right? So some discretization is essentially needed. Okay, so optimization problem is like if you classically look at it, it's a very continuous kind of a thing, right? So you have to convert it into some discrete kind of units, like the lattice points maybe, right? And then there is a possibility of converting it into some mixed integer programming, linear, And there was one more thing, like simulated annealing people were talking about. That's a quadratic approximation, right? So essentially you have something like X transpose QX, you minimize it. And simulated annealing also does some sampling based thing. Yeah, so that is another way.
So in another thing is in many of the cases you may not be interested in finding the global minimum. So suppose that you come across a solution which is energy minimized, then you can cross check whether it is good enough or not. So sometimes you are happy with some solution. So in that case, even if this equivalence, what we are talking about, is not perfect, it may still work.
So hi. So one of the things that I noticed that majority of algorithms that are there are variational. Is there a perturbative algorithm available for that, or if not, what is the problem?
So variational problems are perturbative by nature, right? So you change the parameters and see what expectation values you get.
So what I was meaning is variational algorithm means you're minimizing, you're going to the upper bound of the exact energy, and perturbation you apply some perturbation and try to find out what is that perturbation by perturbative methods. So all the methods that we have are variational, like whatever quantum methods that
no, not all the methods. There are different methods. Hamiltonian simulations.
Right.
So I mean Oracle based and Fourier transform based.
There are some
right.
So question is which one is most convenient in the given the present day quantum computers, which we call as noisy intermediate scale quantum computers. Which one is most convenient? Which one is most suitable?
Right. So coming to that question,
because we don't have error correction yet, qubits are error prone.
So there are two kinds of problems you would like to solve, right? If you are making a quantum analog. So one is the time independent Schrodinger equation, the time dependent one. The time independent, all these variational solvers that you see, the time independent one is essentially boils down to solving some eigenvalue problem, right? And the time dependent one is where you want to see the time evolution, right? So you have those Hamiltonian simulation that are different class of problems, right? So that is different. But since most of the industry related problems boils down to some optimization problem, or even biosciences, I'm guessing, so I mean there could be some time evolution problems also for in biosciences, but most of the problems as we see, I mean coming from the industry is essentially boils down to solving some energy function, like minimization of some energy functions. That's why we come to this this variational problem. But there are some other ways to tackle that as well. You need not always resort to this variational algorithm. So there are these algorithms where you can essentially do some sampling, okay, from a very large Hilbert space. You can do some sampling, you can project your Hamiltonian to that lower subspace, and then do the diagonalization in some classical supercomputer, right? So those things are also there where you don't need variational kind of algorithms.
So just to give you an example, recently we are doing one experiment, something called Falcon experiment. Okay, so in these, so you are applying some perturbation as you said, and then we measure certain observables, and based on that we can calculate what should be the correction to that perturbation. So it's a feedback algorithm. So every time you measure certain expectation value and then give that as a feedback, and this goes in a iterative loop, and the correction is calculated based on that expectation value measurement, intermediate expectation value measurement, and that converges faster.
My question is, we do machine learning, so I want to just relate how the Hamiltonian is formed. So for a machine learning algorithm, we have input data set and target data set. We can define the cost function. Then from the cost function, how it is related to Hamiltonian, how to convert it.
Yeah, I guess you had that question while Professor Senapati was
I'm
presenting.
still not getting the answer.
Yeah, so it's like this. So I'll give you an example, right? So basically your thing is you have an objective function, you want to convert it into a Hamiltonian, right? That is your question. So it's like this. So if you have a problem, right, where the control variables or the the variables that basically you're trying to optimize, right, the optimal points, right? So those variables, if they can be converted into zeros and ones, right, then it's easy for you to convert it into a quantum analog. Okay.
For example, neural network weights, we want to optimize other parameters. The weights. are not binary.
So that is a little different. Neural network weights are different. So I think what I understood from your question is you want to kind of have a mapping between your objective function and the Hamiltonian, right? That is your question, isn't it?
Yeah.
Yeah.
So in the objective function, let's say it is the mean square error.
Right.
Objective function. So I am optimizing or changing the parameters so that mean square error will be minimum.
Yes. So the parameters that you are changing is the x, let's say. Let's say you are some function of fx, right? Minimizing f of x, and the arguments are x, and you are minimizing over x, let's say. So your fx has to be expressed as a Hamiltonian, which has to be Hermitian by nature. Okay, that is one. And this x that you see, in this case the x is basically the states. Okay, so essentially it will boil down to minimization of fx will boil down to some minimization of psi hx, basically the expectation of that Hamiltonian. Okay, so minimization of fx can be mapped to minimization of psi hx, basically the expectation of Hamiltonian h. If your psi can be expressed as quantum states in the form of zeros and ones, then your problem is mostly done. Okay, and the Hamiltonian also has to be expressed in the form of polystrings. Okay, so that essentially your Hamiltonian has to be Hermitian in nature first of all, and they should be expressible in the form of polystrings x, y, z and x, y, z and I. Right? Then your problem is kind of solved. I mean, you can map it to a quantum computer.
So you see, in machine learning, we distinguish 4 types now. So CC, CQ, QC, QQ. So classical data, classical machine learning, classical data, quantum machine learning, quantum data, classical machine learning, and quantum data, quantum machine learning. So all these things are possible now. It depends on what kind of data you have, classical or quantum, what kind of machine learning you use, classical machine learning or quantum machine learning. So as I said, you see, ultimately what is machine learning? There is some input, there is a highly nonlinear evolution, okay, which is neural network or something else, okay, and then there is an output. And now you are training that, suppose handwritten A, whatever, it may be written by any of us, it should give the same output as alphabet A. Right, so that internal nonlinear evolution takes care of it. So that nonlinear evolution is replaced by the qubit evolution. Okay, so that is the map you have to do in case of quantum machine learning. So now there is also another type that is called reservoir computing. So there we don't even need to know the qubit Hamiltonians and all those things. It's just a nonlinear quantum system. Very complicated nonlinear quantum system. Only thing we demand is it should be reproducible. Given same input 2 times, it should give the same output, and then training takes care of it. Yeah. So you have to train properly that 2 inputs of same feature should lead to same output. Ultimately, yeah. So
what is the test data and the training data? How it will connect with the
So you see, let us say that I can give you one example. Suppose you want to make a database of all the movies, okay, and now you also want to make database of user feedback, the customer feedback, people who have watched those movies. I can say that the people are represented by qubit states and movies are represented by quantum operations. Okay. In fact, we did this experiment recently. This is called quantum recommender system experiment. So we can now suppose that some people have some seen some movies, and have based on that they have given feedback. Okay, so they have given rating 1 star, 2 star, 3 star, 4 star, and there are different movies and different users. So now you can make a matrix. Okay. So now your personality is encoded in this, because suppose that for comedy movies you have given more ratings, Okay, that means that you like comedy movies. Okay, now there is a new movie now, which has just been released. Now Google wants to advertise that to you. Okay, so based on your personality, they will generate that rating for you and say that okay, you will like it. Okay, so okay, that's the recommender system, and that's how we can implement experimentally. Like you can say that all the people are represented by the quantum states. You take some register of some size, and quantum states represent people. And quantum operations, you select certain gates, you say that they represent the movies, and then we can find what is the best rating, predicted rating.
I can give you an example, right? You wanted your training data or test data to be encoded, right, in terms of qubit language. I can give you an example. So for example, let's say you have one data point, let's say with n features, let's say, right? That's how you would do, right? So I'm giving you an example. This may not be the only way. There could be several other ways. And every feature would have some value, right? So what you could do is, so this feature value could be in the form of a superposition state, okay? And the features could be the n qubits, okay? That is one way, right? I'm just giving you an example. Another example could be the features could be encoded in the form of a superposition state, right? And the, for example, if you have n features, you will need their log n qubits, like, because if you have that scaling, right? Because n qubits can have 2 to the power n states. So n features can then, be encoded in just log of n qubits, right? So, and then the feature values, right? Then has to be, and that, requires some bit of thinking, like how you can do it. But you can do it. It just requires a little bit of thinking. I don't have ready-made answers. It is like a very interesting. Yes, yeah. Yes. Right. So that is when, see, there are some problems that came up, like solving the traveling salesman problem. Like yesterday I was talking about traveling salesman problem. Like, right now the state of the art in terms of, qubits required is of the order of, let's say, n log n. Like, if n is the number of nodes, there's a higher order binary optimization. So you will need n log n qubits. So with n log n qubits, there is some limitations, like how many you can, how many nodes you can simulate as far as the traveling salesman problem is concerned. But there is another way, like where, there was this paper sometime back, simulating the traveling salesman problem in a single qubit. So how you can do that? So basically, see, you have this block sphere, right? If you consider the qubit as a block sphere, and there are infinite number of states possible. So the question in that paper was like, could we, traverse the block sphere, and then kind of mapping that traversal in the block sphere to the the actual traversal of the traveling salesman, right? So, but the problem there was you needed something called, tomography, quantum state tomography, which is very kind of hard at the moment to do. So there are challenges, but you have to be creative in, how you map it. I think there are lots of people doing this kind of research. Yeah, essentially they are all numbers, right? Yeah, whatever be it, it's essentially some numbers, right? Yeah, so there are some already available kind of circuit you can readily pick and choose that can convert it. That is available. Some libraries are there.
How does this work for dissipative systems like Navier-Stokes, for which there is no standard Hamiltonian formula?
Yeah, that's basically in the area of I would say CFD and all, right? So that's a major thing that we have been seeing. A lot of people asking, can we use CFD problems? So one thing I can tell you is, if it's solving large sets of linear systems of equations, right? If it boils down to that, then I guess there are some solvers available, some variational methods, and there are some Krylov based methods as well, right? So, you may have seen Krylov based methods in your I guess conjugate gradient kind of methods, right? So where you use them to solve some linear system of equations, right? So there are some such methods available right now. Some research is ongoing, but exactly solving CFDs, I mean, there is no answer, frankly. I mean, I don't have an answer to that, frankly. Yeah.
That we can. There are like HHL kind of algorithms which are available. HHL. Yes. But those algorithms has like qubit requirements for those algorithms is huge right now.
Right.
Okay. So that is why it is struggling to solve OD or PD kind of solvers using HHL algorithms.
Right. HHL is one algorithm that solves linear system of equation, but the problem with HHL is, like, you know, circuit depth and qubit requirements is too huge. So they are like mostly fault tolerant kind of algorithms. So basically, when we will have error correction, we can use those algorithms, right? So but for the moment, you have to be satisfied with some evolution techniques or some variational solvers or something. Yeah. Yeah, I'm sure there are, like, so you have to, I mean, I don't know. Okay.
I haven't searched for it, but there must
there are some image see, I mean, if you just search literature, right, there are immense number of papers coming out every day, right, on applications of quantum computing, whether it's image, whether it's speech. All you have to do is just simple Google search, and you will get n number of papers. I mean, and I'll not be an authority on, you know, nobody will be an authority on every paper in every domain, right? So you have to do that search for yourself. Mostly Python. Yeah, mostly Python and Julia.
Hello.
Yeah, so my colleagues, not my friends in fact, Tata, it's not Tata, the Chatterjee group, the TCG Crest in Kolkata, right? They were solving some problems using they have their own variant, some adapt HHL, right? So I don't know, I mean, there are lots of work, but the only issue with HHL is not currently implementable, is the issue. You can of course use simulators and try it out, but it's a lot of circuit depth, and yeah. Yeah, definitely.
We'll take just last question from the madam. Yeah.
Hello.
Yeah.
As you understand that this algorithm is very important to reduce the requirement of qubits, and in the morning we saw that for protein folding problem, amino acids were represented as a qubit, as cubes, and then lattice, and then Hamiltonian was based on hydrophobic collapse or objectified functions. So my question is that for like protein-protein interactions or protein-ligand interactions kind of problems, we have some leads for from experiments and MD simulations. So how to formulate those Hamiltonians, and since we are very new to it.
So the problem is, like, you have to map it to some graph problem, some max cut problem, right? Min cut problem. So some protein ligand connection, right? Is it following some max cut kind of a graph theoretic problem, right? If you can map it to some graph theory problem, there are ways to kind of map it to Hamiltonians.
This node and because this network kind of interactions that we have prepared already, so maybe I will try. Is there any tutorial or use cases?
Yes. I mean, I'm sure ScoopAI AI also has. IBM also has quantumlearning.ibm, like, you know, so learning.ibm. Learning.quantum.ibm. I can share the links. Yeah.
Thank you.
We'll probably share those kind of links. We'll take those links from our industry personals, and then we'll share on the emails what you get usually. Yeah. Please give a huge round of applause for the industry experts. It was such a nice session actually, and I mean, my personal actually, some of the questions were already cleared, how to convert your problem into Hamiltonian and then do the simulations. Yeah, so I would request Dr. G.K. Patra, the host director, Director CSR4PI, to give a memento to our industry expert, Dr. Kalyan Das Gupta from IBM Research. and to Dr. Sumant Ghosh as well from QPy AI. And Dr. Prakriti Singh, yeah, please go. Thank you so much, sir. And yeah, let's disperse for the lunch. And I know you might be having so many questions. And yeah, we can discuss those over the lunch. And after the lunch, actually, we'll have the valedictory session at around 2:30. And then we will go for the visit to the 4PI HPC facility.
I'll share the link.
The lunch is in the NL Belur canteen. Some of us will direct you to that. It's maybe around a 10 minutes walk from here.